Hello, everybody. Rob Maines here. Welcome to the CHIPS Alliance Technology Update. We will start here in about 5 minutes. Welcome, everybody. We will start our spring or biannual update here shortly in just a few minutes while we wait for more folks to join us online. Hello, everybody, and welcome to the CHIPS Alliance Biannual Update. My name is Rob Maines. I am the General Manager of CHIPS Alliance, and hope you can all see my screen with the title of the event. So we're very fortunate today to have a number of different speakers on a variety of topics. Our first one being Mao Han from Alibaba, updating us on the RISC-V CPU update and porting Android to that, followed by an update on the Chisel ecosystem by Jack Koenig of Sci-Fi, the recently formed FPGA or F4PGA work group that we've created, which is championing an open source tool chain, and there's a lot of exciting developments in that arena. Dave Kellett from Intel will be joining us and talking about the Chiplet IP protocol that Intel has been championing and now is in alliance with others in industry to help move that forward. Anant Kulkarni from Western Digital is going to chat about NVMe computational storage processor for both the edge and data center applications. That's definitely an exciting area that is gaining a lot of traction in the industry. We'll then have a great update from the NIST from Brian Hoskins and Pragya Shrestha towards open source models of cryogenic CMOS, which is definitely another interesting advanced technology area. And then Tim Ansell will be updating us on statistics relative to Google's no-cost shuttle program, which is really helping to champion open source designs and move that forward with both Skywater technology and eFabless. And then I'll close out with some final remarks. So, over the past year, we've had continued growth in CHIPS Alliance. We've had a number of different universities join us. We've had companies such as Xilinx, which is now AMD, join us as well. So there is continuing momentum in the open source community. And we continue to work to drive towards building that and to provide an open source ecosystem that participants can utilize free of worry by having it on a Apache 2.0 license. In other words, you can integrate IP that is licensed under Apache 2.0 free from worry to your business or to your university, which is not something that's always possible with different IP suppliers, if you will, or foundations, as I have learned in my 15 months as part of this role. So really, what is CHIPS Alliance about? It's about building an open design ecosystem, and it has many participants, as you can see here on the slide, and it spans all the way specification out through RTL, process design kits, tooling, the actual FI implementation, and standards. So what we're trying to create is an open innovation ecosystem that allows participants to come together and work on hard problems in a collaborative fashion and hopefully accelerate time to market. The notion of an open PDK is actually very important from the perspective that it allows different parties to participate and collaborate very easily. For those not familiar, it's often a real challenge to get an actual NDA signed between a foundry and a given company, and often you have to involve other partners as part of that. So it can become quite a challenge to get that completed in a reasonable time frame, as example. So what CHIPS is all about is creating an open design enabled environment with what I call a catalog of trusted ingredients, whether that come from the implementation framework and the associated implementation design tools, whether that be analog or digital, or if that's from the verification side. That could be the actual architectural, the RTL, the verification model, the properties, etc., forming a verification test bench for functional simulation or for formal verification or for emulation that will allow you to build trusted logical macros or physical macros that can be used by different entities wishing to build up higher level IP from that. A key part of CHIPS, and in many regards what you're hearing today, is updates from our different work groups. So we have a number of different work groups, and these spin up or spin down as necessary relative to topics of interest to the overall community. You heard me mention earlier about the F4PGA work group that we recently started, and also we're going to hear an update on Chiplets from Dave Kellett as well. But there are many different parts that are active within CHIPS Alliance, an important thing. And of course, new topics are always welcome as part of this. And just kind of a shout out here relative to something new that's coming on board. So you notice there that I've mentioned design language as a part of that. And really, some of this you'll hear from today from Jack Koenig of Sci-Fi on the Chisel platform. that he'll be talking about. We also look at other design languages as well, include a lot of the work relative to system Verilog that we've pulled into Chips Alliance, starting from Google and Antmicro. And we're also now looking at bringing in System C that is coming forth from Intel and some of the work that they've done there. So we're really trying to provide a multiple language type of environment that's built up off of a unified hardware data model that allows us to use that to build different types of tools on top of that. So again, I look forward to today's talks that we have. And Malhan is going to be our first presenter today, chatting about Alibaba. And then at 8:40, we'll go on into Sci-Fi. So try to leave a couple minutes for questions at the end of each presentation. So we'll see how that goes and look forward to hearing from folks. So with that, I will stop sharing and turn it over to you. I'll go ahead. It's a pleasure for me to introduce Malhan from Alibaba, and he's going to chat with us today about RISC-V and updates to the Android system on that.
I don't know. Hope you can see it.
Yes, we can see your screen and hear you as well. Thank you.
Okay. Hello, everybody. My name is Malhan. I'm a senior engineer from Alibaba TED and the chair of the RISC-V Angel SIG. Since Alibaba TED reported putting Angel basic functions onto RISC-V in Chiplets last year, more effort have been spent to rebase our previous work on Angel 12 and enable the third-party window modules to facilitate video, camera, and Wi-Fi, Bluetooth related features on RISC-V. The upgrade involved featuring Angel 12 on hardware that has high performance RISC-V processors. We will also provide insight into how to build TFI modules running on RISC-V cores, and building AI modules using high performance codes and software stacks will help accelerate the landing of RISC-V to smart and terminal products. And if we set the massive production of a real RISC-V-based Angel certificate product as our final long-term target, we are still at a relatively early stage towards that. And the RISC-V support of the most crucial component have been implemented with the initial porting project of Angel 10 and have more features that to be expected to present on the system and to meet the execution requirement of complicated user applications. So we are keep trying to enable the missing features by integrating the window modules and the corresponding software stack into the system, and found some extra effort I needed to support them. And the poor IP support on the RISC-V architecture and the incompatibility and the lack of verifications in the software stacks are the major challenges we met while developing the new features. And to the next milestone of adding the upstream of RISC-V support enhancement and the upstream inclusion. We foresee the code quality of the RISC-V support and the fields in test suite verification will be a main blocker to achieve this goal. And the further productization will face challenges of optimization, poor SDKs and application support, and the missing of the reference design. And as I mentioned in the last talk, the Angel ecosystem is huge, and the basic LSP Angel support is only tip of the iceberg. With the tremendous effort in system feature involvement, we have expanded the RISC-V support from basic OSP infrastructure to some core toolset and the third-party libraries BSP this time. By integrating the vendor modules, how implementation, service framework, and user applications, we have proven the feasibility of using RISC-V-based entry device in scenarios like multimedia, signal processing, device interconnection, and artificial intelligence. However, more efforts are required to fill the architecture support blank in the whole ecosystem. We are looking forward to see contributions from more participants. And to accomplish goal of the upstream improvement, we have set a plan of 6 steps to get a clear-cut work scope and lessen the inclusion effort of patch development. And initial version we started with the Angel porting was the Angel 10, and it was followed by the open source development master by about 2 years of development, and we have to readjust the previous Angel 10 patch set on the top of the new released Angel 12, and brought up the launch UI with many RISC-V related changes. And currently, we are currently working on the key features involvement on the RISC-V-based Angel system to ensure that the more test suite can be executed based on the RISC-V platform, and will continuously improve the compatibility and the correctness of the RISC-V support by fixing the test case fields in the CTS and VTS. After the patch refinement for Angel 12, these patches for the external project can directly go to the third-party open source project, while the Angel core components related support needed to be submitted during the development window of the new Angel version. And by the time of Angel 13 release, we can replace the Angel the RISC-V support with the minimized changes and define the core component patches for the RISC-V architecture, and it will the patch set will be ready for submission by the development window of Angel 14. And through the previous work, we also figured out some basic hardware requirements for Angel development. And the hardware platform is expected to have more than 2 CPU cores at 26/9 level to handle the multi-threading of runtime service workload. And the basic system service takes about 2 GB of memory, so it's better to have more than 4 GB memory in the device. And a hardware GPU is required on the device, as the graphical rendering of Angel is based on the OpenGIS. And the board should also get an USB port for ADB connection to enable the fundamental debugging support like logcat and file transition. And if you want to enable the multimedia service in the system, it's better to have an audio output and input, media codec, and image signal processor on device. And the hardware neural network accelerator is also required for running some machine learning models in some complex audio or video process. And to support RISC-V on Angel 12, we developed the RISC-V support on the base of the Angel 10 implementation. And the left column in green are the modules can be upgraded to Angel 12 with small changes, including most of the tool chains, build support, and the system libraries. And the yellow blocks in the middle are the new added features of Angel 12 on RISC-V, including Bazel, Rust, and Angel Studio. And the dark yellow blocks are the architecture-related modules with major changes compared to Angel 10, containing art and Bionic. The red blocks are the vendor modules with little relation to the CPU architecture, which include the audio, video, camera, and other peripheral modules. And next, we will show some we'll introduce the new edit features and then talk about the changes in Bionic and art. And Bazel is the new build system introduced by Android 11. It is used to replace the older blueprint support from Android 10. Compared to the older build system, Bazel is faster, flexible, and simpler. And the RISC-V related changes in Bazel are mostly located in the configurable setting and constraints. And the Rust support is a native development language introduced by Android 12. It has better memory safety guarantee while not reduce the overall performance. It is currently used in some security-related scenario at the moment, and will be used everywhere on C or C++ is currently used. And the RISC-V support for us is mainly located in the target triplet libraries, library search path, and C library interface. And besides the changes in OSP main projects, we also supported the APK generation with the RISC-V API support API in Android Studio. We started by generating the Windows version NDK with the RISC-V architecture support. After that, we integrated this NDK into official RISC SDK and import SDK into Android Studio. And then we get the RISC-V architecture supported in the Android Studio. And we have also successfully running the TF-led modules on the RISC-V cores relying on the Android Studio support. The software implementation of neural network was first integrated into system to verify the API functionality, and finally replaced with hardware neural network accelerator to improve the computation speed of neural network. After that, we added the RISC-V build support for default and generate the demo APK with Android Studio, install the APK through ADB and execute it. And we can see the super resolution example running on RISC-V based Android on the right side, and it can upsampling 50 times 50 low resolution picture to a 200 times 200 resolution picture. And the Bionic support of RISC-V has some major changes in the Android 12 upgrade. The dynamic distribution of iPhone is supported in the new version. It can obtain the hardware capability through hardware cap and dynamically bind iPhone handler through a specific assembly optimization implementation. And the other changes embrace the dynamic syscall generation, kernel head upgrade, and some new support of relocation types. This modification include about 6,000 lines of source code changes from more than 30 commits. And the art is another module with a lot of changes in this upgrade. It mainly includes changes in two parts, the interpreter and the module art. The interpreter uses the same calling constraint as a compiler to save the stack transition, and between interpreter and the compiler modules, and the modularization of artifact, the art project, libcode, and several other modules into a single Apex file and dynamically load it while the initialization of the system. And all these changes result to about 10,000 line of code modification related to GNI and functionalities in ART. And next, we'll introduce the red part of the diagram, the window module integration. With the progress of last year, we have integrated and verified the audio playback, DRM hardware composer, USB OTG, Wi-Fi and Bluetooth, video playback, as well as the camera operation on G12. There are generally three kinds of challenges we are facing to integrate this support to on RISC-V, including the post RISC-V support in window modules, comparability, and lack of verification. Most of our window modules doesn't have a functional RISC-V build script, as they have never been integrated into RISC-V based engine before. Some of the window code have compatibility problem due to the bandwidth, head definition, or API difference. And in terms of debugging, we also met many problems caused by the incorrect configuration, file missing, or compilation errors due to lack of software stack verification on this file. We would like to call for more contribution from IP vendors to improve the RISC-V support in their Android SDK. Then the future inclusion of new window modules will be much easier on RISC-V based Android device. And here we will use the facilitation of video playback and camera as two examples to show the problems detail of window module integration. And here we got 4 key issues we met while enabling the video playback on this file. And the default multimedia service on Android is partially compiled with 32-bit, and the material service and certified XPO can't be generated with the 64-bit only RISC-V support. And therefore, we modify the build script and header files to enable the basic service generation on the RISC-V 64-bit only build. And then many exceptions occurred during the initialization and loading of hardware OpenMax or service, as the compilation flag and the source code haven't been verified on 6-bit platform before, and we have to pay a lot of effort to debug these issues. And in addition, there are several conflicting OS definition in the Android main project and the window implementation. So we removed the config part of the window OS header to solve these problems. We also added support for the address obtaining from the native window buffer to get the final output buffer address for the hardware codec. And the main problem with the camera part enablement is, and the window module only support the RISC build before, and we did a lot of additional work to add the NDK build and change some of the memory allocation and the debug application API in the source code to make the ISP module compatible to RISC Android build, and then modify the ISP pipeline by adding the camera sensor into the device tree, adapt the camera hall to obtain video input from camera ISP. Finally, we can get the camera preview work as shown in the video here. And now we have got an AngelSig running in the RISC-V International Organization on the Software Horizontal Committee. At the moment, it is aimed to coordinate efforts of developers to improve the RISC-V support of Angel software stack and help making RISC-V-based Angel product a reality. And the certain developments can be divided into several domain-specific subfields that can be handled by task groups. For example, the CLAN, GCC, ROS toolchains can be improved under the existing toolchain task groups. And some new task groups can be founded to deal with the deficient of the development tools and application regime. And besides the works taken by the task group, we can also collaborate with other SIGs on some common topics, including the management runtime, graphics, machine learning, and the automotive to enhance the comprehensive system capability on RISC-based Angel. And the RISC-V support of Angel 12 is partially uploaded to the collaborative repo on the GitHub. Now you can look for the source code and rated binary through this link here. And if you are interested in Shantia CPU IP SoC dashboard, you can visit the Alibaba had Open Chip community website here. Products info, technical spec, and the service email and some other information can be found in this web page. And if you want to join us to the discussion, you can also subscribe the mail list in the AngelSig web page. And thank you for your attention. Any questions?
Sorry, it took me a minute to unmute. Yes, any questions from the audience? Thank you for a great talk, Malver. Otherwise, I appreciate it. So I was just, I'm impressed with the continued progress that Alibaba is making on building the software development ecosystem for RISC-V processors in the mobile space. I was just curious, how much involvement have you had from the open source community in helping you on this path?
We've got about 20 pull requests from the open source community during the last several months, and a lot of them come from PLCT, and some come from the Chiplet and several other organizations and entities.
No, that's great. It's wonderful to see the progress here, particularly with the open instruction set based architecture from the RISC-V folks, and then also the open source work in terms of building up the entire software stack. That's very important. So we did have, well, there's been some dialogue here on that. I think maybe the question was answered, but this is from Vishal Dikal, or excuse me if I'm not pronouncing the name correctly. Question is, can we also bring Unix-like operating system to the RISC-V, like FreeBSD? And there was a response. There was a response that FreeBSD already supports RISC-V, as does Linux.
I don't have much background about the FreeBSD's world, so I don't think I can answer this question.
Okay. Appreciate that. So other questions from the audience for Mao? What would you say in terms of building up the overall software stack has been the most difficult challenge that you and your team at Alibaba have faced?
The challenge while we built up the software stacks. So as I mentioned in the section side here, we are currently enabling a lot of system features in the Android system, and a lot of these features are based on external vendor modules support, and we find that the support was relatively poor compared to the vendor module support on ARM or x86, and some part of the system service is not compatible to RISC-V because some of the architecture information is missing, and some definition from the system files have some conflict with the headers in the LSP project, and a lot of source code is not verified on the RISC-V based architecture Android system before.
That would be a definitive challenge for sure. There's another question from Vishal here, noting that there is an Indian Shakti processor which is working on RISC-V. Do you have any opinion on it?
Indian Shakti processor. Is there any further information about this processor? It's used for high performance processing or some low power kind of applications?
Yes, I don't know. We'll see if Vishal provides any further information. So one other question, I noticed that you went from a C++ development environment to Rust. I'm just curious how that migration went for you.
Can you repeat the question?
Yes, I saw that originally work was being done in C and C++, but then you migrated to Rust, and I'm just curious how that was.
It's some common change in the Android 12 system, and it's currently only the script related modules is compiled with Rust at the moment, and it is some kind of improvement to use memory safety language to help reduce the potential of memory leaking, and some other memory bugs to improve the system robustness and stability. And the RISC-V related changes are the things we did to support the RISC-V Rust toolchain for RISC-V, including the target Chiplets support and some related library interface support.
Appreciate that. So I do have some questions here from the audience. Do you have a target goal of when an Alibaba product using this infrastructure could be released? I don't know if that's something you can comment on. That's probably a set. Go ahead, sorry.
Using this infrastructure. All things we done is only the basic enablement of system features at the moment. We are sure to have some kind of product in the near future, as we will get the final target, the RISC-V-based Angel certificate product as our final target, and we will surely make some plan for it.
Thank you. So next question is, have you considered an ARM to RISC-V translation layer instead of recompiling?
Yes, we did some research on that, and this question has previously discussed in the NGSIG, and it's some kind of library called libhoudini on the x48 architecture, and we may do some research like using the cmos-like implementation and some related researches as a basic, and try to implement it in the future.
Okay, so we have time for 2 more questions. So one is, you showed a copy of a tablet in the video. What hardware is that? Manufacturer, SoC source, if you can comment.
It's only the internal test chip of Aliport at the moment, and
okay, go ahead.
This purple is not open to public at the moment.
Okay, thank you. Then the final question is, it's a question about lack of verification, and just if you could clarify what was meant by that.
Lack of verification, I mean,
I think that's relative to third-party software.
Yeah, I mean, this software are not haven't been run on RISC-V architecture or Angel-based RISC-V architecture before, on Angel-based device before.
Thank you. Well, Mal, thank you so much for preparing this chat today, and also to Alibaba as well. I think there's some really exciting developments and progress that you all have made in relative to RISC-V and building the software stack around it. I know it's late there in the evening, so I do appreciate you staying up and talking with the audience here today too. So thank you so much. With that, I'd like to introduce our next speaker, who is Jack Koenig. He is with Sci-Fi. He's a senior staff engineer at Sci-Fi and an open source maintainer of the Chisel 3 and Fertile projects. His interests include hardware design, simulation, and programming language. So with that, Jack, if you'd like to take it away, appreciate it.
Yes, sorry, I also was struggling to unmute, so
yeah.
Let me share. Okay, can you see my slides okay?
Yes, we see, and we can hear you just fine too.
All right, great, thank you very much. So thank you for that introduction. My name is Jack Koenig. As mentioned, I work at Sci-Fi, but I'm also one of the maintainers of the Chisel and Fertile projects. And you can see down there, CWG TAC member, which stands for Chisel Working Group Technical Advisory Committee. So let me now introduce what is a Chisel Working Group. And to do that, I always have to begin by introducing what is Chisel. Now, many of you may have seen these introductory slides before. I apologize, but I find every time I give a talk about Chisel, there are always at least a decent number of people who have never heard of it. So I'll first talk about Chisel. So what is Chisel? It's an acronym for Constructing Hardware in a Scala Embedded Language. And I'm kind of distinguishing constructing here because people often think about hardware description languages where you write code, that describes your hardware, and then that is directly translated. In Chisel, things work a little bit differently. So I'll touch on that in a minute. Now, Chisel is a domain-specific language where the domain is digital design. It's a little repetitive, but you can think about Verilog as a domain-specific language where the domain is digital design. But I do want to specify that Chisel is not high-level synthesis nor behavioral synthesis. So often when people see Chisel code, they think in terms of HLS, like C to gates, which is a fairly popular approach where you can just write C code or C++ code, and that will be directly synthesized into hardware. That's not how Chisel works. And that's why I underline that constructing word. And I'll get to more of that in a minute. Because what you're really doing in Chisel is you're writing a Scala program to construct and connect hardware objects. And Scala is a general purpose programming language as distinguished from a domain-specific language. Scala is similar to Java, C++, Python, Swift, whatever general purpose languages you're familiar with. And it has a lot of modern language features like parameterized types, object-oriented programming, functional programming, and static typing with powerful type inference. So in the world of programming languages, there's a lot of features that one might refer to that make a modern programming language. And you can see even older languages like C++ and Java moving in this direction. But Scala is one of these kind of more recent languages, recent-ish. I mean, it's over 2 decades old now, but recent-ish languages that has all these powerful features. And what Chisel is really intended for is writing reusable hardware generators. So what we want to do with Chisel is to make hardware, or especially digital design, more productive. And the way you make people more productive is you have them write less code. And the way you write less code is that you have the ability to reuse code or to use libraries, right? If you think about when you write code in Python or Java, say, you don't usually have to go re-implement the functions to open files on disk, or even command line parsing library or command line parsing. Usually you can just use a library. So it's that type of reusability that we're trying to build for hardware. So now a brief introduction to what Chisel kind of looks like, and I think it might help if I have a pointer. Okay, so this is what I might call Verilog-like Chisel, where you can write things that are very similar to what you might express in Verilog. So yes, the syntax is different, but the basic principle of what you're doing is the same. So in this case, I have a simple module similar to Verilog. I have my ports, which is just an input and an output, which are both uints, which you can think about as just like unsigned bit vectors. It's parameterized by bit width, just like you might do in Verilog. And I have 2 registers and then a sum at the end. And so this is, as mentioned in the class name, a moving sum 3 FIR filter. The question that immediately comes up when you write something like this is, well, what happens if I have more than 3 points? What if I want to weight my averages? What I really want is a generic FIR filter where there's different types of parameterization based on what you would like to do with it. And so what Chisel enables, so on that previous slide, I showed that you can write Chisel kind of like Verilog if you want to, but you can also write much more powerful software generators where you can parameterize it using the full power of the Scala programming language and then construct your hardware in that way. So in this case, the FIR filter is parameterized by not only the bit width, but also the values of your coefficients and how many of them you have. And so as you can see here, we have multiple, we have a serial in, parallel out shift register, which are these Z's right here. So each cycle, it shifts to the next one. That's what this little chunk of code does. And then we actually have these multiplications with our, parameterizable number and value of coefficients. So we can multiply each delayed value from the input with the coefficients, and then we sum at the end. And so if you think about what this really is, this is meta programming where you can, you're writing a generator, you can reason about the fact that you're generating hardware, and you can make decisions based on your parameters to decide what you're trying to build. And what's really cool about this is now you have that same filter I showed you before is this filter with a certain parameterization, but you can also make other things like just a 1 cycle delay, or you can make a 5-point triangular impulse response filter. And so there's all kinds of things you can build just from the ability to have greater power of parameterization. Now, all of this is really cool and really important, but it's not enough. So what we've realized over the last few years is that sometimes, there are very platform-specific or application-specific changes you need to make to your RTL in normal design flows. For example, if you're running on an FPGA, you may want, some type of scan interface or interactive debug or snapshotting. Some of these features are supported directly by the FPGAs, but often the features aren't as powerful as you would like, and you may want more, and you may need to modify your RTL to get that. Other examples are, when I say reusability, what that means, it doesn't just mean that I can write something once in my design. It means I can write something once, hopefully forever, and I can use it on an FPGA or in multiple different technologies, right? For anyone who's done ASIC design, you know that oftentimes you have to do a lot of specialization for your technology. Some of these examples being SRAM macros, specialized layouts, clock generators, different SRAM macros with their own specialized layouts. And so what we realized is that we need a software stack but for hardware. So originally with Chisel 2, you had kind of these libraries built on top, and then you had Chisel kind of in the middle, and then different applications like simulation, FPGAs, and ASICs underneath. But borrowing from software where you have a compiler with specialization for different platforms, we broke Chisel up into a front end and a compiler called Fertile. And I do want to always note that this picture is leaving a lot of details undiscussed, and that there's a lot of work that goes on underneath. We are only doing one small piece, and that these these projects like Verilator and F4PGA, Open Road are doing a lot of heavy lifting underneath. The idea of just being this full software stack built on top of that. And so a little bit more about this software stack that we have built is called Fertile, and it's an extensible hardware compiler framework where you have transformations that take a design that comes out of Chisel and then can lower it down to Verilog, applying transformations as well as custom transformations. It's written in a very modular way, and it has robust metadata and annotation support. And I'll get back to this more later, but this enabled all kinds of custom extensions to really show how flexible this hardware compiler is. Okay, so with that introduction, the projects of the Chisel working group are, as I've mentioned, Chisel and Fertile especially, but there's a few others. There's Chisel Test, which is our testing framework. There's Treadle, which is kind of a simulator for Fertile. It's nowhere near as performant as Verilator, for example, but it has a lot faster startup time. So for unit tests of only, tens, hundreds, a few thousand cycles, it's like much faster than having to run Verilator compilation and even GCC. We have the bootcamp and the template. We have some older projects that are, I would say, as of now deprecated. So the IO testers have been replaced by Chisel Test. DSP tools, I'm not fully saying they're deprecated, but we are looking for maintainers. So if you use DSP tools, please reach out to me. And a diagrammer, I think, will be folded into Fertile itself. So the separate project is kind of will eventually be deprecated in favor of just going to Fertile. Okay, so now some highlights from what's been going on. So some of this I talked about at the last at the October update, but I want to note that that was when we had just done RC1, and now we've actually released many of these things, and they're being used in production and have been now for the last 6 to 8 months. So vector literal support, just the ability to make vectors of things more easily. This is just simpler syntax. I'm just noting that these are some of the quick things, and I'll go into some other things in more detail. Scala 213 support. This is really helping get up to the most up-to-date, or the not most up-to-date version of Scala, but a more up-to-date version of Scala. We have now a decoder and minimizer API, so this is really helpful for expressing, well, decoders especially, but any type of like declarative decoding style logic. And this is really helpful and has espresso integration. Source locator compacting, just to make the source locators in the emitted Verilog look nicer. Lots of performance improvements. No, that didn't go quite how it's supposed to, but Chisel itself is about 40 to 50% faster, depending. It depends a lot on your particular design, because as I mentioned, Chisel being a generator, you're writing a Scala program. The user can write things that would run slow, but for typical designs that we have at Sci5, it's gotten substantially faster. And Fertile itself has also gotten quite a bit faster. And we've added new utilities to the standard library, and an open source contribution of an RTL-IL backend is exciting, just to show kind of integration with other open source projects. RTL-IL is the intermediate form used by Yoast, which is a very, is the open source synthesis and tool, very, very useful. And so it's just cool to see that type of integration. And then Professor Martin Schuberl has updated his digital design with Chisel book. There's now a 3rd edition, updated to Chisel 3.5, and just noting that this book now has versions in Chinese, Japanese, and Vietnamese. So that's all very cool and very useful. And of course, see the release notes for all of this on GitHub, because this is some lightning highlights of smaller things, and now I'm going to talk about some bigger things. So Chisel test, our testing framework, has had a lot of improvements. The way you can interact with the design is simpler now with Scala types. It has improved barrel simulation performance. So previously it had to use inter-process communication, and now it has a more direct integration. The Barrelator backend now supports dumping FST instead of VCD. That's a simple but convenient thing for many cycles. VCD can get those files can get very large. I mentioned that Chisel IO testers is deprecated, so there's a compatibility API to help migration. Simulation constructs can now be annotated. I talked about the extensibility of the compiler, and this is a piece of that. Assert, assume, and cover are no longer experimental. There's simulator binary caching, which helps speed up when you run lots of Chisel tests. And then there's support for bounded model checking, which I'll talk about on the next slide. So Chisel test now has kind of native, if you will, formal verification support. So for any of you who've done formal verification or have heard of it, you know that it's kind of always assumed to be really difficult. And it can be difficult, but as with most things, good tooling and sensible defaults can really help here. So when you have, like in Chisel test case, it looks very similar to a simulator-based flow, even though you're actually doing a formal check. A really common thing in formal verification is having a passed function. And so there's certain safety here that the defaults can make work a lot better. And by that, I mean, a common issue when you do formal verification is that you have you ask for the value of some wire or register from a previous cycle, but during the hardest part of formal verification is coming out of reset. And oftentimes trying to deal with that fact can be complicated. So sensible defaults in Chisel test help make the pass function safe, and automatic reset guarding is really useful to deal with some of these reset issues. But of course, if you are trying to verify your actual reset, you can disable the default behavior here, or just for that test. And it has close integration with the simulation flows. It has the same basic APIs, same IDE and tooling integration, and it automatically will give you your counterexample through a waveform by rerunning it through a simulator. And so just some technical details. There's an SMT-lib and BTOR2 backends in Vertal, and this works with your standard open source model checking tools like Z3 and CBC4, or not model checking, SMT solving tools. And then you should please check out Kevin Laufer's paper on this, where he goes into greater detail. But just as a quick picture, you can see here that if you've written much Chisel, this you are testing in this case the behavior of an SRAM, and you're looking at I believe this is looking at the read under write behavior, and using the previous cycle, checking if you had a write and a read and the addresses were the same, then the output data should match the input data. So this isn't read under write. This is just if you do a write and a read. No, this is read under write. Sorry. If you do a write and a read in the same cycle, should you get the same data? And so this is, this can be checked formally, which is very cool. Okay, so another big feature that this is kind of undergoing development at the moment, but is available in Chisel 3.5 is definition instance. So historically, Chisel elaborates every module and then deduplicates. And this is fine most of the time until you start building large things. So for most users of Chisel who tend to be building, smaller, 32-bit in order cores, RISC-V cores, it doesn't matter that much. But when you start building big things, it starts to matter. And so this is a new API to help us distinguish between the fact that you may want to define a module, as in its actual implementation and all the details of the module, but then you want to just merely instantiate its public API instead of having to, re-elaborate it each time. And so this has huge performance improvements for large or hierarchical designs. It composes with our annotation flow, but I do want to note that this is experimental. I think it works really well for what it's supposed to do, but we want more out of it. So there's a lot of development going on here. That doesn't mean you shouldn't use it, because the current APIs are fine. We just need more, basically. But the basic idea being, you can, instead of just instantiating a module, you can create a definition of one and then instantiate it multiple times. And an alternative API that we are still considering is the ability, this looks more similar to how you instantiate a module normally without having to create that separate definition object. And so this is an alternative API that we're still considering. Okay, so now the feature that I'm the most excited about, but this is very much a developer. As a developer, I like this, as those other ones are probably more exciting for users. But data view is something I think is very cool. It comes from the observation that often users want to manipulate a hardware value as if it were of a different type. A good example of this is an AXI style flat bus interface, which we all know from common AXI code in Verilog and from the standard. But when you write things in Chisel, you tend to write things in a more structured way. And so you would like to manipulate, you would like to give that flat bus interface, because that's what most Verilog users expect, but you would like to manipulate it as if it were more structured. And so this allows treating objects of one type as another. You can, this sounds a lot like a union or like a cast, but it's a bit more powerful than that. So I usually draw the analogy to a view in SQL. And I don't want to touch too much on the details of how this works, but what's so cool about this is how many things can be implemented by this one primitive. So we were able to implement seamless integration with Scala types. So this won't mean a lot to you if you don't ever write Chisel, but these parentheses, as they are in many languages, are tuples. And so tuples are a built-in Scala collection. And for all of our hardware operations like connection, we implement them on our own hardware types. But this data view feature allows us to take these tuples and view them as if they were hardware and then do this connection. And so this looks very simple. It looks like it obviously should work. But for those who've used Chisel in the past, you might know that this is kind of a difficult thing to do well, and data view enables it. Bundle upcasting is really important for when you have some inheritance relationship between bundles, which you can think about as structs, and you'd like to take the child bundle and manipulate it as if it were the type of the parent bundle. It helps enable that. It enables user-defined mappings. So those were all built-ins, but you can create your own mappings, and don't worry about this code here, just showing that it's possible. And then a perennial ask in Chisel is people create an IO bundle, and then they say, but I don't want the IO prefix in my Verilog. So this same feature that did all those other seemingly unrelated things also made it possible to implement a version of IO where there is no IO prefix. So this is in 3.5.3, which I'm intending to release on Friday, but it allows you to, create Verilog, have a bundle, create an IO from it, but not have the IO prefix in the emitted Verilog. So that's very cool. All right, so now I'm gonna backtrack a bit to this slide, which you may hopefully remember, where I talked about how we need a software stack for hardware. And I mentioned that Fertile has very robust annotation support. But another thing that we've determined during all this time is that it's a lot of work to build and maintain a software stack, especially with only a handful of developers. And we have this whole power of metadata and annotations. I have this picture of kind of like a solar system here, because there's a whole universe of what people can build with the annotation support. And we also have a whole bunch of custom infrastructure doing a lot of heavy lifting here to make all this work. And there's kind of a telling picture over here of LLVM of kind of a future direction that we are going on, which is that LLVM has this new kind of project called MLIR. And what if we could share infrastructure with MLIR, which is kind of like, you can think about it as a generalization of LLVM, rather than LLVM just for emitting, as intended for mainly C++ and for emitting assembly. What if you could just share some of the more common aspects of what compilers need? And again, and what if instead of arbitrary unstructured annotations and whatever arbitrary data the user wants, we could try to constrain and better, to better define and understand what data people are manipulating and capture that information in multiple dialects. So instead of a single IR to rule them all, which, even LLVM found that doesn't work out, because if you look at how, Rust, Swift, and other languages built on top of LLVM, they have their own IRs on top of it because it can't represent everything they need. So similar problem in hardware, we have different potential IRs that we would like to represent. Okay, so now just briefly, what is MLIR? It stands for multi-level IR. And it's, as I said, a generalization of LLVM. So it's like you take LLVM, all that infrastructure in the compiler, and you throw away the fact that you're just compiling, things that look kind of like C++, and you're just compiling to assembly, and instead just say you're compiling whatever IR you want to whatever you want. And so it's infrastructure for building new compilers. And as such, it is suitable for multiple IRs at once. It's written in C++ and extremely performant. And so that's MLIR. That's like the base technology on top of this new project called Circuit, which is, we all love our backronyms, is Circuit IR for compilers and tools, pronounced Circuit. This is an LLVM incubator project. So unfortunately, despite my suggestions, they're part of LLVM instead of Chips Alliance, but it does make sense as they are, part of the LLVM repo. But this is compiler infrastructure for generating Verilog. And so Circuit really is a collection of hardware dialects. Importantly, for the Chisel community, is there's a Fertile dialect, but there are many others. There's a System Verilog dialect, although I'm giving a star. It's not that you can parse arbitrary System Verilog. It's more that there's a System Verilog emission dialect. So Fertile can compile the System Verilog and then emit System Verilog. There are other RTL dialects, including combinational and sequential. And then there are, there's much like, while Chisel and Fertile are part of this, there are other dialects going on too. There are people working on elastic silicon interconnects and handshake protocols and high-level synthesis and all these other things that people need compilers for in the hardware community. And so really, it's a collection of tools for compiling circuits. Fertool is a drop-in replacement for Fertile. And this is a picture from their website, but it's just showing how there's all these different projects going on. And you can see Chisel compiles to Fertile, which goes through the Fertile parser, but there's a whole bunch of shared infrastructure here between these different dialects that different people have built. And then those get compiled down to the System Verilog dialect, exported to Verilog, and then we can get System Verilog out at the end. But there's all kinds of other stuff going on here, which is very cool. And hopefully, as this project continues to mature, we can leverage even more of it. So on the mind of anyone watching this talk right now, what does this actually mean for Chisel? It's that there's a next generation Fertile compiler that is almost there. It's getting very close. We are about to switch to it as our production flow at Sci5. It has much faster compilation, 5 to 10 times faster. It uses a lot less memory, 5 to 10 times less. It has better Verilog emission. This better Verilog is always it's always an ask, and it's always a very complicated thing to do, but they have worked very hard and are doing a very good job and are continuing to improve it. All of that is great. Like, all of that is beyond enough for such a cool new project, but that's not even the best part. The best part is that this is also a robust new platform for new features. So the whole point here isn't just to build the same thing we've already built. We could have made the existing flow, maybe not that much faster, but somewhat, like a decent amount faster, and we could have made it use less memory. But instead, this new infrastructure also makes it's a much better platform for adding new features. And so we haven't started adding those new features yet because we're still trying to get the new platform into production. But starting in Chisel 3.6, we're going to have native support for Circuit to make it easier for users to use, instead of it being kind of like a go figure it out. We'll have flows to help you do that. And then starting in Chisel 3.7, we plan to start adding features directly to Circuit that would have been hard to do in the existing flow, with new dialects for things like verification and whatnot, and whatever new features we want to add. Now, I was trying to come up with a good diagram for this slide, and the easiest thing to show is compile time. So I'll show the compile time. This December here is Chisel and Fertile, at Sci5 with a design from today, but using the compilers from December, and the compilation of a large out-of-order core. And you can see that this compile time has decreased from well over 600 seconds to about 150. And that includes this 7.6x improvement on the Fertile part of it. And that's by using this next generation Fertile compiler. But also, that's obviously the biggest, by far the huge chunk here, but don't sleep on the fact that even Chisel got a lot faster. You can see here that it's not quite 2x, but close to 2x faster than it was only 4.5 months ago. And this is a combined speed up of 4.3x. So these are the today changes that are a few things, like we need to be using Circuit to get all this benefit, but a lot of this stuff has gotten a lot faster even in the last few months, which is very exciting. Okay, and so that's all I really have of content. And so I'll show my usual community slide. Please go to chiseling.org if you want to see what's going on. And there's a community page linked to on the website. You can chat with us on Gitter. You can ask questions on Stack Overflow, and you can watch old talks on our YouTube channel. There are, I don't know, probably about 100 or more talks there at this point. So there's a lot of stuff to look at. And I also want to say, because I just gave all that mentioning of Circuit, check out their website as well if you're interested in hardware compilers and seeing what's going on over there. Cool, that's all I have.
Hey, Jack, thanks. That was a great talk. I am always impressed with the amount of progress that you and your working group make in helping advance the state of the art of an object-oriented based hardware design description language. So I really appreciate that.
Yeah, thanks. It's been a good few months.
Yeah, no, you guys are doing great. So I was in particular intrigued by the inclusion now of formal verification as part of this. As you correctly noted, formal is typically a very challenging area for design engineers. And of course, as you know as well, I'm sure that there are some problems that there's just no way to tackle with functional simulation, such as with Verilator or comparable commercial solutions. But I just kind of curious as to the work involved to be able to include formal type attributes in the language and how that went or evolved.
Yeah, that's a great question. So, part of it is so there are many things that make formal verification hard. And it's, I would say that the first part, which is the simplest one for Chisel, is that, Verilog is an extremely large language. It has something like 4 times as many keywords as C++, and I don't think anybody considers C++ a simple language, let alone what simpler things do. And so Chisel, by having much fewer constructs, makes it really easy to model formally. So that's step 1. Now that's easy. That kind of comes for free based on how Chisel has always worked. But 2, which is really the hardest part, is you need to represent the things you're trying to represent formally. And I think there's a lot of ongoing work there. Our primitives now are still very simple. It's just assertions, like basic assertions and like past operator. But it turns out you can do a lot with that, at least for simple designs. And one cool thing about formal verification is that if you do it hierarchically, you can verify a small piece, and then you can leave that piece out when you verify a piece around it. But it is, I would say this is, we're not exactly like, that's not necessarily our heaviest area of innovation, but it is something that we are trying to do more of and help mature the open source flow.
I appreciate that. So I have a question from Dave Kellett, and Dave asks, how would you recommend first-time users get started with Chisel?
Yeah, so I would strongly urge you to go to the website and especially come chat with us on Gitter. It's a great place for basic questions, like for new user questions, I should say. We have lots of people there asking such questions, and several people will help you out. The main thing to look at is the Chisel Bootcamp. So it's a, I can't remember what they're called, a Jupyter notebook. So it makes the setup simpler to just try things out and see, the basics of how it works. And it's, written in prose to help you get an introduction. So Chisel Bootcamp, and come chat with us on Gitter.
Oh, that sounds great. So I have a question from John Lytle. Does the Chisel community have a working group targeting process device specific optimizations in the tool chain? For example, fertile to Verilog transforms for FPGAs, different standard cells, etc. And I happen to note, actually, being a technologist myself, that you did mention some different attributes that you had to change relative to the design for different target technologies.
Yeah, that is a great question. I would say we have some, maybe not as much as we would like. Like there's a lot more work to do. But we do that at like built in, we do it for memories. So we have a flow to take the Chisel memories, which are functional, and swap them out with a user provided platform specific memory or target specific memory. Now we need more of that. We have done similar work for clock gates internally at Sci5, and I think it's now part of the open source. I believe that type of work is part of the open source circuit, Fertile compiler. So my answer is some, maybe not as much. We don't really do standard cell stuff. We're not a synthesis tool, but we do, at least for things that are obvious and need to be specialized for certain platforms like memories and clock gates, and we can continue to expand that definition a bit. We do have some built-in support there.
No, that's great. Thank you again so much for an excellent talk. I really appreciate it and all the exciting work. And just a final comment is that Martin Schroebel's book on Chisel is available. It's in the chat there. You can see it. You can actually download it if you're interested in it. So that sounds like a great resource. So thanks again, Jack. Really appreciate it.
Yeah, thank you.
Our next speakers will be Michael Gilda and Carol Gugula from Ant Micro, and they're going to be talking about the F4PGA open source toolchain that is a recently formed work group as part of CHIPS and looking at bringing the FPGA community together. So Michael, you want to take it with Carol?
Yeah, it seems that I have some issue with screen sharing.
Could you just share the presentation with Rob, and if he could just flip the slides for us?
Yeah, I will do that.
I can do that. Okay, I see it.
Yeah, standard Zoom on Linux issue.
It's okay. I am almost with you here.
I would help Carol out, but I actually have the same issue on my computer. So
it's all right. Yeah, no, it's. Apologize, folks. Let me just hear this. Is that working?
we can only see click to exit full screen. Oh yeah, now we can see it.
Can you go
Great.
to the first slide?
I mean,
Yes.
Yeah, thank you.
all right. So I'll get started, I guess. So today we're going to announce the creation of a new group within CHIPS Alliance that deals with a lot of different topics, all of them FPGA related. The key topic is the interchange format that we've been developing as part of the group, but that's definitely not all of the stuff that we're working on. And I'm going to co-present with Carl, who's very involved in this effort from the technical side. I'm working more on the, of course, marketing and dissemination and collaboration side. So yeah, if we can flip to the next slide. Just a few words about us. So we're coming from Ant Micro, and we're basically building things with open source, helping people use new design methodologies and create new workflows and build awesome things using the great stuff that open source is giving them. So if you go to the next slide, you'll hear us saying open source a lot. And the reason is that we try to find ways in which people can scale their efforts with open source. And CHIPS Alliance is basically about the same thing. We believe that hardware developers can get the same kind of collaboration, the same kind of benefits from open source than software people can. And of course, we're already seeing this with RISC-V, we're already seeing this in many areas, but this is still not the predominant way of thinking. So we're trying to push this as hard as we can in areas such as FPGA. And if we go to the next slide, as I mentioned, this corresponds to the mission that the CHIPS Alliance has. And the breadth of the entire group covers a lot of the topics we're working with, including, of course, cores and different kinds of IP blocks that together constitute RISC-V based SoCs. Well, not only RISC-V necessarily, but predominantly these days, of course. We work with tooling, we work with lots of different topics, and within those areas, we lead a bunch of efforts. And one of the efforts that we are leading is, in fact, the F4PGA group that's concerned with a number of topics in the FPGA space. So in the next slide, you'll see the layout of what the CHIPS Alliance does, and that's already been shown. But the new bubble in here is the F4PGA group, the one in bold that we're going to talk about today. In the next slide, you'll see our logo. We have kind of designed a whole kind of branding system for the F4PGA group, and you might kind of recognize, of course, this from a previous effort called SymbiFlow. And SymbiFlow was, of course, a pretty kind of big effort involving multiple parties and so on. But one of the things that it didn't have was this kind of supervision, you could say, this kind of structure that the CHIPS Alliance offers. So we came up with, a way to kind of mature this group into a more formalized structure, into something that can be governed within a larger ecosystem of tools and of systems. We call it the F4PGA group, which stands for Free and Open Source Flow for FPGA. And the goal of the group is to drive open source tooling predominantly, but also IP cores, also research and other kinds of systems within the FPGA area. Most importantly, perhaps, the group involves not just different kinds of people and companies interested in this topic, but three kind of distinct pillars that we're leaning on. One of them being academia, of course, that kind of leads a lot of the research efforts. Industry as a very important part, where again we consider us part of this particular pillar, and this is based on practical use. And FPGA vendors, which we believe are, of course, a necessary part of such a group, and we're very happy to actually kind of be representing all of those three groups. And as I mentioned, we have a lot of different focus areas, but kind of some important ones need to be mentioned. One of them, of course, is the open source toolchain, previously known as SymbiFlow. So now it's the F4PGA toolchain. Then we have the FPGA interchange format, which we'll be kind of delving a little bit into today. Tools like FPGA performance framework for, well, measuring the performance of different kinds of tools, and many other things. And so if we go to the next slide, as I mentioned, the important part to understand here is that the kind of the new rebranded and kind of reborn effort is specifically focusing on integrating different perspectives, on making sure that kind of the group represents different perspectives and makes all those things work together. Academia, of course, is extremely important for us because we need a lot of research. We believe that open source opens the door to different kinds of research and novel approaches. So that's obviously the kind of things that researchers like to work on. So that's already kind of yielding some fruit, and we'll kind of talk about it later. But generally speaking, the research part is very important for us. Actually, it's probably one of the key drivers for having this effort set up in the first place. And of course, academia also makes sure that people are taught how to work with these kind of flows. University of internships, they have different kinds of programs where the tool chain can not only be developed in terms of like research, but just used and taught and so on. So we're looking at academia to help extend the tool chain in various new directions and get it adopted amongst new engineers. The second pillar would be industry, and industry, of course, provides the real world use cases. That's kind of extremely important because without the real world part of it, it's very hard to do something that's significant, that's meaningful, and that really changes the state of the art. Also, industrial use kind of improves the robustness and the general reliability of the tool chain itself. It's not just a research tool, it's a practical tool that's being used in real products. And in fact, the tool chain is really used in real world products being developed and rolled out as soon as this year. So keep your fingers crossed. But generally speaking, this practical aspect of F4PGA is very, very important. But last and not least, we also have FPGA vendors. And this group is also extremely important to us because without the vendors, it's kind of much more difficult to work with these kind of topics. Having them on board is a substantial difference from before, where we can jointly collaborate in building out the entire ecosystem. We can actually reach the end users. We can kind of put the tool chains in front of the users, not as a kind of a renegade alternative to the official tools, but also as a kind of officially supported and even if alternative, kind of unfrowned upon methodology of working. And also, quite simply, since it's the FPGA vendors developing the FPGAs themselves, naturally, their assistance in kind of targeting new FPGA targets, planning, providing information about the devices themselves, all of this is very valuable information that definitely helps in kind of pursuing this effort. So going to the next slide, as you can see, we have a bunch of current members, most notably, of course, AMD, who's joined us recently, I mean, in the part of Xilinx, in supporting the open source toolchain and the interchange format specifically. We also have QuickLogic, who have been kind of working with the open source toolchain for a long time now. We've helped them adopt a completely open source end-to-end perspective on the toolchain. And in fact, the primary type of toolchain their users consume today is open source. We of course have Google and Micro. We represent the industrial part, and kind of a lot of the development work is being done by our companies, as well as universities such as University of Toronto, who is developing the variable routing tool, which is an important part of the toolchain, but also others who either use it, develop in various directions, or teach classes such as BYU. So all in all, of course, we're looking to get many more vendors on board. We're talking to quite a lot of other groups that are willing to join our effort, and looking at how they can contribute and how they fit into the picture. But overall, there's really great interest, and I think that over 2022 we'll do really good progress there. So I think that's the end of my part, and I'll leave it to Carl to explain a bunch of the technical items within the group on the next slide.
Yep, thank you. So as Michael mentioned, one of the biggest effort of F4PGA is actually effort on building a fully open source toolchain for FPGA chips for FPGA development. So our goal here is to provide an end-to-end flow that is vendor neutral. We of course have some backends that target various vendors, various FPGA vendors, various chip vendors, but they are packed in a way, they are wrapped within the toolchain in a way it's not really visible for end user. So we can think of it as you use like compilers for software. You don't really use GCC in a different way if you compile something for RISC-V or ARM. Maybe some like switches or flags pass to the compiler, but nothing, not really much, not really more. Yeah, so you just use the toolchain more or less in the same way. So with this effort, we tend to switch FPGA development from like a hardware centric, where people were actually collecting blocks of some black boxes or things like that, or pre-built cores to create a bigger design. We want to actually move everything into like code-driven, software-centric development, where you script everything and you scale everything with powerful cloud machines. When you spawn multiple instances of the toolchain, building bits and pieces and then combining them together in the end. Also, the openness aspect of the open source aspect of the toolchain sparks all the researchers, all the people that want to play with the toolchain, want to adapt it for our special needs, and can actually, be creative and change the software for their needs. As Michael mentioned, this effort was previously done under umbrella of SymBiF organization, but we rebranded that to F4PGA and moved everything into auspices of Chips Alliance. So everything right now is moved there. If you go to Chips Alliance GitHub, you will find the code. And if you want to learn more about the toolchain itself, you can visit our webpage. And in the next slide, you can see the list of currently supported targets. So we do support Xilinx right now, AMD 7 series FPGAs, and those are pretty well supported. We can build quite complex design with the toolchain. QuickLogic EOS is free, and actually that's the toolchain that is used for this platform, for this FPGA. So if you are actually using this chip, you're probably using our toolchain. We also support a few FPGAs from Lattice. Those are Closing NX, ICE40, and ECP5. And more is to come. We'll probably hear about that in the near future. And in the next slide, we can see the structure of the toolchain. We actually divided that into two parts, into front end, like synthesis for synthesis tools, and back end, those are place and route and bitstream generation tools. So for synthesis, we use Yosys. That's a pretty popular and well-known synthesis tool. And for backends, for place and routing and generating programming file for certain targets, we use either NextPNR or Verilog routing, and then a selected projects with a set of tools that allow you to create the programming file, create the bitstream that you can actually upload to the device. And even here in this slide, in this block diagram of the toolchain, you can see that there are at least two place and route tools that can be used. There is only one synthesis tool, but in reality, there are more synthesis tools and more place and route tools. Maybe not open source, but proprietary, but still there is something. So there is this ecosystem is pretty fragmented, and every tool implements some features that can be reusable, and it would be really nice to actually combine them together and use them in a way that you can switch between them seamlessly. So to actually address this problem, we've created something called interchange format. If we switch to the next slide, you will see a very, very nice logo of this project. And interchange format is actually an effort to provide common description between various tools, either proprietary and open source tools, for describing FPGA devices, and providing a way and mechanisms for actually switching between the tools within the flow. So constructing tool chains by combining various tools from various vendors or various projects. And it doesn't really matter in the end if it's proprietary or open source. Of course, we prefer open source, but still you can use that. So the idea here is to make the tools in the end better by lowering the entry cost, by lowering the barriers. Because imagine a situation where you are academia researcher and you are working on a, let's say, placement algorithm, and you have an idea of the best placer algorithm ever invented in the world. But to actually test it, you need still synthesis tool, and you need still routing tool, and some kind of a bitstream generation flow. So without the rest of the flow, you can only place something, do some like statistics, and tell if it's better or worse. But you cannot really test it in hardware. With interchange format, you can use your algorithm, write the design in interchangeable format, and use it later with various tools that are already in the market. And this is very, very, something that changes the way we can work with the tools. The initial development of this format was done in collaboration between ourselves, Google, and Xilinx, which is right now AMD, and we continue working on the format itself. So if we switch to the next slide, we'll see some basic information about the format itself. So we describe the format using a schema defined with Cap-and-Proto library. The whole schema is open source, and you can see it on GitHub. If you go to Chips Alliance GitHub, you can find the schema there and simply use it. There is also a repository providing some tests and then some quick start guide on how to use it. We use Cap-and-Proto because it's pretty mature library. It has stable API and implementation for like various languages, so you can adapt it with your flow quite easily and just start playing with it. And if you switch to the next slide, we'll see like some code snippet actually taken from a physical netlist schema implementation. And physical netlist is something that describes fully placed and routed or only placed design. We also provide two different schemas. One is for describing device resources. This is used for basically defining what FPGA chip has inside. So what's the target device actually provides, what we can use, what kind of resources we can use, and the tools need to know that to be able to perform their work and run the algorithms. And the third schema that we define is logical netlist, and this one is actually used for describing an abstract digital circuit that we get after the synthesis. So basically, after you go from a RTL code or some kind of a abstract code through optimization, through through elaboration, and you get quite abstract description of the circuit. The idea is that each step is interchangeable. So if a tool implements certain feature, you can just switch the tools in the middle of the flow, and that's the greatness of this approach. So if you switch to the next slide, we'll see what's exactly there right now. So we have one end-to-end flow that is fully operational, and we perform tests with that. So it's Yos's synthesis. Then we write interchange logical netlist. Then we use next PNR for place and route. Then we write physical netlist, and we can use rapid write with Vivado to write a bitstream, or open source bitstream writer using FPGA assembly language. The FPGA definition, the device definition is actually taken from rapid write, which is open source front end for proprietary Xilinx tools, and this tool is actually developed by Xilinx, and they contributed to the effort with this tool. So the plans for the next few months, and this is actually going pretty well right now, is to exchange the flow with support for VPR, or some code and some support is already landed there, so we can run end-to-end flow for some like smaller designs right now with VPR, and it works. So it's just a matter of making it more robust and better, faster, fix all the bugs, and just make it work for any random design. And if you're interested more in that, you can refer to Xilinx blog or Google blog, which we helped to write. If you go to the next slide, I would like to show some other tools that are part of F4PGA efforts. One of them is something called FPGA perf tool. So we are working on the tool chains. We are developing new algorithms. We are developing new formats for actually playing with FPGA flows. So we needed a tool or a mechanism or a way of actually comparing the results, of actually tracking if we are, doing better or maybe doing worse. How do we compare against other tools, against vendor tools, and so on. So we developed a tool called FPGA Perf tool, and this is, I would say, more like a framework for running a set of tests against a set of test designs against various tool chains, gather as much info as we can, and info in terms of like resource usage, like host computer resource usage, like CPU time, memory, disk, and so on, but also quality of results, like how fast the design was in the end, how many target FPGA resources we used, and so on and so on. So we run it daily in a public CI on GitHub. It's also a part of Chips Alliance GitHub, and we generate a dashboard where you can simply go and see like historical results and some graphs showing, if we are going in the right direction, maybe wrong direction, if we are slower, faster, and so on and so on. So that's pretty nice to understand what's happening, what's the best choice, what's the best tool chain right now, and if there is any regression. And if we go to the next slide, the other tool that we've been working on is something called FPGA Database Visualizer. So this one is more like tool for documenting how the FPGA designs, how the FPGA chips look like inside. So most of the vendors, they do provide some kind of a viewers in the software, but those are not really, you cannot really, have a one single place to check what's inside, how the devices look like. FPGA Database Visualizer is a vendor agnostic tool that can actually grab a database. It's right now we process open source database from various projects that are there, for example, from VPR place and route tool, format used by VPR place and route tool, and we can draw an interactive, render an interactive web-based visualizer where you can simply check what is where, how the blocks look like, how big the FPGA is, where are the memory blocks, or certain types of cells that you're interested in. As I said, this tool is more for us to understand what's inside, and of course for documenting the chips for wider audience and for people who actually are going to start their work and start doing some FPGA designs. If we go to the next slide, there are, of course, more than only those projects. We work on many smaller tools that we need within our tool chain. And those are, for example, FPGA assembly parser. FPGA assembly is a format, textual format that is one-to-one compliant with what is in the bitstream itself, in a programming file for the FPGA. So this one allows us to basically analyze bit streams and see if there is something wrong and so on. And it's intermediate step in many flows just before the bitstream generation. We also maintain YOSYS plugins providing various extensions to YOSYS itself. One of them is, for example, a system Verilog extension, which provides a lot of system Verilog features that are not supported by default, and this is provided with use of external parser called Sherlock, and intermediate representation called UHDM. I actually talked about that some time ago in one of the Chips Alliance workshops. And there are many other tools, smaller, bigger, and so if you are working on any project around FPGAs, please take a look at what we have there. Maybe you will find something that is very interesting and useful for your project. And I will give it back to Michael.
For the next slide, please. If we summarize, as you can see, we're building an ecosystem, you could say. The Chips Alliance is working both on FPGAs and ASICs, and the work group that we talked about today is specifically focused on FPGAs, which we believe a fundamental kind of entry point into the ASIC space, the prototyping platform, a kind of younger brother of the ASIC domain, let's say. And the interchange format, I think, is a particularly interesting topic because it shows how collaboration between many entities, which includes the FPGA vendors themselves, is not only a possibility, but a necessity. And we believe that's really the case for any kind of ambitious effort like ours. And we think that it could be worthwhile to try to transplant this success into the ASIC space in the future. So hopefully, as we've shown, having an interoperability format is very, very useful. And in fact, like we could see also in the previous talk, and kind of, I assume it's going to be a recurring theme, joint standards, joint formats, all of this is very useful because it gets more people working together. We showed that practical use cases of the stuff that F4PGA is doing is already possible. So as I mentioned before, we have products being built with the toolchain. We have kind of real serious research going on and a lot of promising new ideas. And so what we want to do with F4PGA is to enable, kind of new software-driven approaches to FPGA development. We want to kind of enable machine learning-based approaches to different kinds of topics. We want to help people do rapid prototyping. And all of these things, of course, can be done with closed source tools as well. But we believe open source lends itself especially well to these kind of activities, because software people that we really need to lure into the FPGA and ASIC space to help us out kind of scale those topics, they prefer open source typically. When they're building things, they want open source building blocks that they can reuse and develop and improve, right? And that's what F4PGA is really trying to do, get hardware to be more like software. And on the last slide that we have for today, we have a call to action for you to join us in the effort. And of course, we have a bunch of media, such as the mailing list, F4PGA-WG, like for all the Chips Alliance work groups. We have a channel in the Chips Alliance Slack, so go ahead and join it. If you have Slack, join it through Slack. If you prefer IRC, there's an IRC bridge. We have an invitation, and we'll share those slides later. We have an invitation link that you can use to join the Chips Alliance Slack. You can follow us on Twitter, or please do follow us on Twitter. The handle is very simple, F4PGA. And of course, check out the code on GitHub. There's a lot of repositories. The main repository is simply F4PGA. And from there, you should be able to find all the links to the relevant places. So with that, I'll hand it back to Rob.
Hey, thanks, Carol and Michael, for a great talk on the F4PGA work group and all the activity there. It sounds like a lot of exciting stuff is going on, and I totally agree that FPGAs are the way to help make hardware design more malleable or readily adoptable, similar to as what's occurred in the software space. So I think that's wonderful. So let's take a question or two here. So there's one from Adrian Prosvocal, and this is there a clear statement from AMD Xilinx about their official position towards third-party tools supporting their FPGAs? Obviously, someday one of their legal team may wake up and complain about this impacting somehow the company revenue. Current status is very uncomfortable. So I don't know if that's something you want to comment. Go ahead, sorry.
Yeah, I mean, obviously I'm not a lawyer, but as the disclaimer goes, but you might kind of imagine that Xilinx/AMD participating directly in the work group is definitely a good sign. So if kind of anyone had a chance, a reason to worry, I assume that would have been in the past and not currently, right? The whole point of the effort is to show that we can and do collaborate with vendors, and we don't really deal much with the what ifs. It's all a matter of industry adoption. It's all a matter of momentum. A lot of the great stuff that we're building is also, of course, benefiting the vendors themselves, right? It's and in fact, the interchange format as an effort is supported and kind of welcomed by AMD/Xilinx because it's kind of helping their own research effort, right? It's, as Carl said, it's supported in their own framework called RapidWrite. So I think the development of this is kind of to everyone's benefit. So we're not altogether very worried. I don't believe anyone will ever, kind of issue a formal statement about this because, I don't believe there is such a thing you could do to make sure everyone feels super comfortable. But I think, like, in terms of making people feel comfortable, joining CHIPS Alliance, joining the ForPGA work group it makes me feel comfortable anyway.
No, appreciate that. Thank you for the answer on that. So I'll just add one comment here, and this is just about the material from the presentations today. So we will make those available as well as a recording of that today. So to keep us on schedule, I will end the questions on this particular topic. But thank you again, Michael and Carol, for this. I think it's great progress, and look forward to the collaboration folks moving forward on this effort.
Thank you.
So thanks. So our next speaker is Dave Kellett, who is a research scientist from Intel. He's a researcher working on pathfinding for programmable logic technology. Dave is currently developing chiplets and chiplet technologies to enable a new model of electronic system development. Earlier at Intel, Dave was vice president of IP engineering. So Dave?
Thanks, Rob. Can you hear me okay?
Yes, I can hear you and see your slides as well.
Fantastic. All right, I'll go ahead and get started. So I'm working on a project that I'll talk about in a minute here that we really entered in with two objectives. And the first one was, how can you make it easier to build chiplets and multi-chip package devices? Sometimes when you're building two chips, it ends up being more work than one chip. And so the real effort is, how can you make this just simply easier, a better development experience? The second piece was, at the same time, we want to be able to advance the state of the art in chiplet design for interfaces, for protocols, for functionality. So we really had these two objectives. So I'm going to talk about three things today. Die-to-die interfaces, including AIB 2.0 and the newly announced UCIe. I'm going to talk about a new chiplet SPI open source hardware IP that we have, and new chiplet AXI open source hardware IP that we have. You folks may have seen that about a year and a half ago, Intel was awarded the SHIP program by the United States government. And the purpose of the SHIP program was primarily to give the government access to Intel state-of-the-art packaging capabilities. But at the same time, the reason for using these advanced packaging technologies is so you can build systems out of chiplets. So the SHIP project also includes developing chiplet interface standards and protocols. And we are using these IPs that I'm going to talk about, the chiplet AXI and SPI IP, in a chip proof of concept chiplet and multi-chip package that's part of the SHIP program. The idea is if we build this factory, this capability to assemble multi-chip packages, that we want to make sure that the customers of this factory have the tools, the IP, and the technology so they can build high performance products. In summer of 2020, we announced AIB 2.0. It's our second generation die-to-die interface. You can see some of the key metrics on here. The bandwidth per wire, the architecture supports going up to 6.4 gigabits per second. Now this is times, it is many wires as you want to put in an interface. So this could typically go up to 8 terabits per second on an interface. So it supports a variety of bump densities for micro bumps all the way down from 55 down to 36 micron. And you get the other metrics as as go on, such as reduced energy per bit because you're trying to send more bandwidth across. It's going to use more power, so we want to at the same time reduce the energy per bit to kind of keep that normalized. And since we have existing 1.0, this provides backwards compatibility when you use the 2.0 interface. So the 2.0 spec is part of the CHIPS Alliance. It's a CHIPS Alliance release specification, so you can see it at the GitHub repository that I'm showing here. And we also have 2.0 RTL for the AIB 2.0 PHY in this repository here, so you can check that out as well. And this is actively being developed as we go through our proof of concept. Now, you may have heard that early last month, there was an announcement on the Universal Chiplet Interconnect Express, and this is an idea to create an open ecosystem of chiplets, of technologies. It's a specification organization, a lot like CXL. So they don't build products. It's not open source or anything. It's a spec group. Now the UCIe key performance indicators include per wire rates up to 32 gig. So there's a little bit of an arms race on how fast can you take the individual wires. So this is way up there. The UCIe specification will include details on how to interoperate a UCIe interface with the AIB-based chiplet portfolio. Now, since this is a spec organization, each UCIe participant determines their own product roadmap and their own product availability. It's not part of the UCIe consortium. And you can download the spec, and I did it myself. You can go over this address here and take a look at the spec and see what's going on. And you can see the industry representation that joined up with UCIe. And at this point, I kind of want to take a pause here to kind of talk about people who've been following die-to-die interfaces in the industry. And I just kind of want to go through and identify a few things here. So things that AIB does well. AIB showed that a high-performance wide parallel die-to-die interface is practical for volume production. And 5 years ago, this was not obvious that wide parallel was the way to go, because there was still a lot of thought that SerDes might be the way to go. AIB built a multi-vendor, multi-process portfolio of chiplets, and AIB led with open source digital and analog design. So we've got the AIB PHY, the digital design there. At DAC back in 2020, I talked with the folks from Blue Cheetah about an AIB analog generator, and we've got open source protocols, which is the subject of the rest of my presentation today. Now, the other folks in the industry, you folks might have heard of the ODSA bunch of wires. So one thing really that I think the bunch of wires folks did well was that they showed that a wide parallel die-to-die interface on standard packaging is interesting for cost-sensitive applications. And we know that there are IoT, wireless infrastructure manufacturers that are extremely cost-conscious. Standard packaging is generally less expensive than advanced packaging, and that's the ODSA bunch of wires folks really showed that you could do the same approach on standard packaging. And then finally here with UCIe, the thing that UCIe has done really well is it used the Intel CPU's industry influence to align everyone on UCIe. And so you can take a look at the folks on here. There's AMD on here. Marvell has joined this. Broadcom is part of this. And so really it's become just a broad, wide industry adoption that I think a lot of people were waiting to see before they really went full force into building chiplets. So I just wanted to say a little bit more about Intel and UCIe and AIB. And so one of the questions is will Intel continue to develop products using the current AIB specification? The answer is absolutely yes. We have products out today. We have products that have not released yet that use AIB interface. And we have customer products that are part of the SHIP program that use the AIB interface that are in planning, in various stages of development and release. The second question is, will UCIe support AIB? I kind of touched on this earlier. The UCIe specification has an appendix, and it will include details on how the UCIe implementation can interoperate with AIB-based chiplets. And what are Intel's plans for AIB going forward? So we at Intel, along with the other folks that are on the previous page, we're committed to UCIe. We will eventually migrate AIB applications. The way I look at this is design starts this year, design starts next year. AIB is the way to go. Design starts that are out there, 2024 timeframe. UCIe is definitely something to consider. We know that the AIB 2.0 specification is being used now, and that ultimately those the key performance indicators that I mentioned earlier, that chiplet developers will want to take advantage of that, and ultimately this will converge on UCIe. Now into the open source chiplet protocol IP. So I want to talk about SPI. Now, folks are probably familiar with SPI. What we built is a simple protocol on top of the SPI signaling. SPI is widely used in the industry for ADC DACs, for peripherals, for just general low bandwidth die-to-die communication. Our experience is that everybody who builds a chiplet needs some way to either configure the chiplet, boot the chiplet, get things going before you have your high bandwidth wide parallel interface going. And this has been almost universal that people have used this. Now, the problem is that, as I'll mention earlier, or coming up, SPI is just these set of wires. And so it does, streams of reads and writes. Everybody has done something on top of that differently. And so you end up with kind of an interop challenge. And if you're an FPGA on the right-hand side, that's great. But if you're an ASIC, having a whole different set of ways of doing reads and writes on top of SPI is a little challenging. So we have provided open source for both the SPI leader and the SPI follower. Folks who, all you got to do is check the Wikipedia page on SPI, and you'll find different terms for that, master and slave. We at Intel, we don't use those terms, so we use leader and follower. Our chiplet SPI follower plugs into the AIB hard macro for AIB configuration, and it plugs into what pretty much everyone needs is a control and status register application or a firmware download or something like that. Now, just as a refresher here on chiplet SPI die-to-die signals, you've got a leader. So in our case, we support up to 4 followers. We have 4 select lines. We chose to have separate meso lines for ease of debugging. You could put those all on tri-stated and have a single wire there. We've also defined that the data units going across MOSI and MISO are 32-bit double words. Now, this is simple, right? Why are we even having this conversation about SPI? It's so simple. Well, really, the trick with this is that you need to frame commands and data on top of this MOSI and MISO. Now, when you have these chiplets, you've got a variety of roles here. And we have what I call an initiator. So this is somebody who's really kind of the system controller deciding, okay, now I need to configure these chiplets. I need to bring them up. I need to get their high bandwidth interfaces running. So we have the initiator. Then we have our SPI IP, which is the leader IP and the follower IP. And then you have targets. The targets are things you're trying to do things to. So the initiator drives the SPI leader, and it has a simple address read-write interface with 32 bits of write data and read data that go between the initiator and the SPI leader IP. So now, you recall, we're doing all this because really our objective is we want to do writes and reads to follower targets. We've got our system controller, that initiator over on the right side, what it's trying to do is talk to these targets over here. And the typical targets are AIB PHY control and status registers. This is how you define exactly how the AIB is configured. Folks who are familiar with AIB know that it has 1-to-1 modes, 2-to-1 modes, 4-to-1 modes of different multiplexing modes. So that's one obvious thing. That's what we're using it for, is configuring AIB interfaces. And the second one, we have a need for with some of the protocol configuration with other application-specific functions is a application register block. So we've provided a very simple general-purpose chiplet control and status register block. You folks can take a look at that, and you'll see it's obvious that you might want to put something a little more sophisticated there that does sparse address decoding and that kind of thing. But it's very easy to add. So this is kind of really why we created this, so that you could have a common way of talking to these chiplets. So our chiplet SPI IP is out there on GitHub. You can see it's under the Chips Alliance repository under a repository called AIB-protocols. And you can see there it is, SPI AIB. So you can go take a look there and check out the user guide and find the source code there. I want to say that the code is functionally complete. We are doing an extensive verification using code coverage metrics that it has about another month and a half to go to complete. We don't know of any open bugs with it. We do use the GitHub issue tracking mechanism. So if anybody has questions or issues with this, please go ahead and record that. Okay, now I want to talk about AXI4 protocol IP. One of the key piece of feedback we received on our various chiplet projects over the years was, great, you've got this PHY here. We need protocols. And this is the next area of interoperability after the PHY. You know, the protocols are the data link layer at the least, and it could go higher. We've built protocol adapters on each side that convert standard AXI4 streams, standard AXI4 onto the AIB PHY data wires and then convert it back. So applications A and application B think they are talking AXI4 or AXI4 stream, depending which variant you're using, and they don't see what's going on under the hood with the AIB PHY. So we provide the adapter IP for both sides, so that the mapping between the standard AXI interface and the AIB PHY wires is understood. So we kind of take a look at, you know, why did we pick AXI? And you know, my experience at doing protocols and IP is that the applications drive the protocols, not the other way around. I think there's always been a desire, could you come up with a universal protocol? But you just can't, because sometimes what you need for, let's say, a real-time system where you want to turn around in nanoseconds a response because there's something hostile flying at you, you need to do something about. You may not want to use a distributed shared memory coherent protocol. You might want to use something very lightweight instead. So this is typical of streaming applications here. If you've got a ADC DAC, you might get just streams of samples that every clock it's got another bundle of samples. Similarly with an optical transceiver, suppose you have an Ethernet MAC there. Now you have the MAC to application interface, which is generally aligned packets at this point. This kind of interface looks a lot like AXI4 stream, and that's a conclusion we made several years ago. Now there's a different mode of operation. This is where you want to do reads and writes. So memory applications are a perfect example of it. You still need high utilization, you need high efficiency, you need low latency. This looks like AXI4. Almost all of our the commercial memory controllers, for example, use AXI interfaces. And then there's another strange one, which you may, after you've brought up your chip using SPI, you may want to have a faster path to controlling your chiplet. And so using a AXI4 Lite for control and status registers over your high bandwidth bus will give you that faster response. You don't have to go through the SPI serialization. This looks like AXI4 Lite. Now, I just want to give a little bit here on AXI. It has a valid and a ready. The valid says that the data is good, the follower should take it, and ready says the follower is able to take data. So this is the flow control, pretty standard. Now, that picture on the previous page assumed that the leader can respond to the follower in the same cycle. The follower says, I'm not ready. The leader cannot move on to the next word of data. So the leader has to be able to react within the same cycle. Now, if you take a look at this path here, I'm going through my adapter, I'm going over the PHY, I'm going across the package, then back through the PHY and the follower adapter. Straight AXI, the same cycle response is not going to work because there's a clock phase difference between the leader and follower, and there's pipeline delays, a crossing between the leader and follower. So that's the reason we have these adapters for AXI4 to do the die-to-die operation. And it allows and takes care of these phase delays and pipeline delays. What we've implemented is a credit scheme. This is a pretty standard protocol scheme. So the leader can send to the follower when there's a credit available, and the follower returns a credit when it has consumed an entry and it's vacated. Now, here's where it gets really interesting. You take an AXI4. AXI4 has these 5 channels: the read address, the read data, the write address, the write data, and the write response. They call them 5 channels in AXI terms. We have to map these to a TX set of wires and an RX set of wires. So we got to do this 5 channels down to 2 channels, and then expand it back out on the right side, back to its 5 channels. So the follower says, hey, I'm just seeing commands coming across from an AXI leader. So we've defined a packetization, and this is an example here I have where you have a header type that tells you which kind of message is coming across. You've got your address, your various AXI parameters here. Then the next word be a piece of write data that carries across 64 bits. You've got your WID indicators, and you've got things that are flow control. The push, it's a valid indicator, and those are the things that use up the credits. Now this is configurable. AXI has a lot of flexibility about how wide your data bus is, your address size is. So this is an instance that we're using on our chiplet, but we've built a generator as part of our open source code that allows you to select exactly something that matches your AXI configuration. Now, I just want to say there was an alternative way of thinking about this. Is you could just take these 5 channels, the AR, R, AW, W, and write response B, and you could just fold them, saying, hey, look, there's really about 214 wires. I'm just going to time multiplex those 14 wires over my PHY. And so you can see 214, it's going to take you 3 80-bit cycles to get 214 signals across. Now, so we did a efficiency study of this. So to do a write single, and the way we've done it through packetization, it takes 2 full rate cycles. If you were to fold it, it takes 3 full rate cycles. Now, once you start doing bursts, the situation gets much, much worse, because the AXI4, a lot of these wires are not used all the time, definitely not in a burst. And so you're wasting your bandwidth if you multiplex all the wires across, once every 3 cycles. So this is the benefit of packetization. Now, when you're using AXI4 on die monolithically, the slow utilization doesn't really matter, because your wires are small, a lot smaller on die than they are even on advanced packaging. And so the packetization is definitely provides this utilization advantage. We've also done some other interesting things. AXI4 Stream, if folks are familiar with this, it's really a one direction data transfer. Now, some of those applications I showed, like the optical networking, the RF ADC DACs, they're bidirectional. So we will pack a leader follower pair, two pairs of those on a single channel, because the channel has TX and RX. So you can pack going each direction to maximize the AIB channel utilization. And so this is something we absolutely use because most all of these applications that we're working with, in fact, all the applications we're working with for ADC DACs, for networking are bidirectional duplex. So our AXI4 IP is out here on GitHub. It's that same AIB protocols base repository, and it has the AXI4 memory map. That's the pure AXI4 and the AXI4 stream. So these are both already out there. They're in the same state, that they're function complete. You can go check the issues here on this. So I took the snapshot. There was a few items to do on it, but we believe it's function complete, and it's just finishing up verification. So in conclusion, there's this famous Gordon Moore quote from his 1965 paper where he articulated what we know as Moore's law. He said something else in the same paper, that it may prove to be more economical to build larger systems out of smaller functions, which are separately packaged and interconnected. So he predicted that chiplets would make sense, and chiplets are being used to build larger systems, just as Gordon Moore predicted. And we believe that we're advancing chiplet interoperability with the open source hardware protocol RTL. So at this point here, I think I'll pause and see if there are any questions. Rob?
Hey, thanks for a great talk. I'm a big fan of the chiplet technology that Intel has provided to the community, and I think it's a definite enabler for innovation. While we wait for questions that come in from the audience, I don't know if you comment on, I'm just kind of curious, has there been any uptake in the usage of chiplet technology by hardware startups, and what might that look like?
Yeah, one of the two startup, let's say, I'll focus on IR Labs. So they're a startup based in Santa Clara that they publicly had a paper at Hot Chips a couple of years ago with Intel about using a wide parallel AIB die-to-die interface. They implemented their own version of SPI. So this is kind of how we got inspired to say, hey, look, if we could do a common read-write protocol on top of SPI, then we wouldn't have to implement the same thing differently on all these chiplets. So that's one public case. I think the other folks that I'm really working with now are large companies that are building chiplets to connect up to other devices, most often FPGAs. And so that's big name defense companies.
Oh, that's great. I know last time I'd asked about support relative to commercial tools or proprietary tools for chiplet design, but I'm just curious, has there any work been done on open source tools for chiplet design?
That's an interesting area. I think there's a lot of things in the CHIPS Alliance that could be applied to this. Chisel is kind of chiplet or SoC independent. I think a lot of those efforts could be applied to it that are not specifically chiplet based. Some other area that we're working on, and I'm sorry, this isn't open source, it's proprietary, it's security IP for chiplets, because once you've disaggregated your device, you've created a new attack surface, which is this die-to-die interface. And what can you do to protect that? What can you do to authenticate that a chiplet that's been put in your package is a legitimate and not a counterfeit or malicious chiplet? So that's another area that we're working on is chiplet security.
No, that's great. Thank you. So that wraps up about the time we have, Dave. So I appreciate your talk on this, and it was very good. Thank you. So our next speaker is Anand Kulkarni, who is a director in the CTO's office of Western Digital, and he's going to be chatting with us about NVMe computational storage processor for edge and data center applications. So Anand, if you're available, I'll let you take it from here.
Thank you, Rob. Thanks for the opportunity to talk. Let me just share my screen a second. apologize for that. 1 second. Hi, good morning, everybody. I wanted to talk a little about accelerator platform that we at Western Digital would like to present as essentially a platform on which we can implement NVMe computational storage ideas. And the platform itself was originally built as a compute accelerator for video transcoding and machine learning applications. And since then, we have tried to veer it towards a prototyping platform for computational storage applications. And we'll talk about the first two cases and then a little more in detail about what our intent is in using this for computational storage. So the platform itself is essentially based on a Xilinx UltraScale MPSoC FPGA, and it's built as a U.2 form factor device with a power envelope that matches standard NVMe SSD device, about 25 watts. And as you can see, essentially the key component being the Zinc, the Zinc FPGA, we have attached to it about 4 gigabytes of DDR RAM and a couple of peripherals that allow us to essentially use it as a general purpose development platform for a variety of applications. And we've tried to build it in such a way that it should be possible to use it both as a vehicle for development as well as completely manufactured production-ready unit if once we develop the application fully on it. And this is basically available today as a video transcode accelerator from the Xilinx via the Xilinx website. So the primary use case that we started for this board was that of a video transcode accelerator. The second use case we came up with was used as a AI inference accelerator, and the inference accelerator we developed it in partnership with Mipsology, and we can go a little more detail about that later. And the third key use case we would like to target for the device is as an NVMe based computational storage device. The video transcode accelerator application essentially uses the video decode unit that is present as a hard IP within the Zinc FPGA, and it allows us to take in a high resolution, high frame rate video stream and scale it down and then re-encode it as a variety of different resolutions and frame rates. The API to this device is essentially as a plugin to FFmpeg. So essentially, you as a customer, they only need to use FFmpeg with slightly customized input parameters, and FFmpeg in turn offloads the video stream decode encode logic, the ladder, off to the device itself. As I mentioned before, it is available now as a Xilinx part number. And the key benefits you can see in this chart here is that the performance-wise, the device performs better than 16 or 32 core x86 CPUs that you might want to use prior to this accelerator being available to you. So it translates to fewer instruction cycles on the CPU, fewer stall cycles on the CPU, fewer reduced requirement for DRAM traffic on the host CPU. And at the same time, the performance that you get out of this is scalable because you could have multiple of these accelerators available in your server system. And this basically, the reason I wanted to highlight this is it shows the potential for computational storage in a system where if you have data, in this case, for instance, if the data is coming from largely a storage device, then it makes sense to try to push this compute acceleration closer to the storage. And this shows to us the potential value of computational storage itself. Even though this device here is expected to be direct attached on a PCI bus to the server, I think we can foresee a system where if this was available as an NVMe device, we could keep it closer to the storage where the video streams originate from. This the device is also significantly better even when you consider the power versus power performance ratio, and you can see that the video transcode accelerator performs significantly better than any standard x86 CPU that you might want to use for the purpose. The second use case here is as an ML accelerator, inference accelerator. This is in partnership with Mythology Incorporated from France. Here, all of the inference is done on the FPGA-based system, and you essentially take a trained model that has been trained either on the CPU or a GPU subsystem, and the software stack converts the model into an int8 or int16 model and offloads all of the inference to the FPGA device. And this allows us to give, again, significant performance comparable in some sense to standard GPUs that you may get, but lower because the power envelope of the FPGA board is limited to 25 watts. But in terms of power to performance, you will see that they are the numbers are quite comparable to equivalent generation GPU systems. Once again, this is a system that works on a direct attached PCI bus, but if you were to imagine that the same performance could be the same application could be offloaded to an NVMe based system, you could again foresee a system where the device would be located closer to the storage subsystem and get additional benefits of reduced power and traffic on the network or PCI fabric. So this brings us to the real idea that I wanted to present here, which is to use this exact device as an acceleration platform for NVMe-based computational storage. And what we are chasing here is to use this board as a prototype platform for NVMe 4191, which is a proposed standard for computational storage. The idea here in TP4091 is that we can the host application can build and download and execute kernels built as eBPF binaries and offload them to run within a VM inside the computational storage device. In addition, we could also download hardware kernels that actually include custom RTL for the application that the host wants to offload or accelerate on this device. What we are building in effect to support that is an NVMe controller that can actually do both. That is, execute hardware kernels as well as execute software binaries that again invoke software libraries that are made available in the device. So what we do is we have an NVMe target controller functionality split between software and hardware, and the software portion is malleable enough that we can very quickly adapt to new command sets and new proposals in the NVMe standard, reflect them very quickly, and be able to prototype ideas for both the standards committees proposals themselves, as well as for applications that might want to use them. And the accelerator, the ideas for the hardware, for the offload of the host application functions, those could be also prototyped quickly, either as purely software accelerators or hardware accelerators with drivers that make them available to the eBPF binaries. One of the benefits of running this as an NVMe device is that if you locate them close enough to the storage devices, let's say NVMe SSDs, then you can think of using peer-to-peer DMA to transfer data from the storage devices directly into the accelerator device, and thus avoid consuming resources on the host for either bounce buffers or PCI traffic or DRAM traffic or CPU cycles, when all you're doing is transferring data really from the SSDs to the device for compute, and then you only have to manage the results of the compute by transferring them to the host for further functions. So one of the things that we will support is using peer-to-peer DMA to transfer or exchange data between peer and NVMe SSDs. As I said before, because this device has both significant compute capability, CPU general purpose CPU compute capability, as well as an FPGA fabric in which you can instantiate any accelerator features, we can have a very elastic boundary between hardware and software as you continue to develop applications or benchmark them for new ideas on what we can offload. And as the implementations mature, the boundary between what is done in hardware and software can move and allow you to further optimize what is the best way to do run the application. In this case, for instance, the shell that provides the NVMe target controller functionality itself, for instance, what we did is one approach is to say that because bulk of the value of such a system comes from being able to implement custom hardware accelerators in the FPGA fabric, we wanted to minimize the amount of fabric that is used to implement the NVMe functions. So what we have in our example reference design is essentially an NVMe target controller implementation that does just the bare bones hardware, uses the bare bone hardware resources to implement NVMe, and bulk of the NVMe functions is actually implemented in software that runs on either the R5 processors in the Zinc or the A53 processor cores in the Zinc device. And that enables us to offer keep almost 70 to 80% of the FPGA fabric available for any accelerator that you might want to implement. very briefly, the target applications that we are developing here are for video analytics and database acceleration, and ideas for what we could do for accelerating genomic type workloads. So I wish I had a little more detail that we can show here, but the first reference design that we are working on is an implementation where for the acceleration of TF-Lite. So what we do in that implementation is the software library that the BPF VM exposes to the kernels is actually a compiled version of a TF-Lite compiled as a library. So you can imagine the host application can invoke TF-Lite on any data that it sends to the device. The second step there is that we implement a small hardware accelerator called VTA, which stands for a versatile tensor accelerator, and that accelerator IP is implemented as RTL in the FPGA fabric, and the TF-Lite library in turn invokes VTA to offload some of the more compute intensive functions in TF-Lite, operators in TF-Lite, and offloads them to the FPGA based accelerator. And what we would like to show with that design is the ability to quickly partition a given offload function that the host application would like to offload, partition them between hardware and software, and be able to make the best of an optimal implementation that also is very flexible, as well as quick to sandbox or prototype in the sandbox development environment. The second application that we would like to show is database acceleration, where we so in the first application, the TF-Lite application, the idea is the whole application, the TF-Lite application itself, is offloaded to the computational storage device. Second idea for database acceleration, the idea is slightly different, is that the bulk of the host application is really running on the host, and it is only offloading specific portions of its workload to an optimum computational storage platform. And in this case, what we'll do is the hardware portion of the accelerator will be doing some minimum functions like string search or regular expression search, or potentially some specific sequential search operators. And the software library will involve implementing some subset of the SQL queries that a database might need. And the host application will actually understand which portions of its own query workloads is compatible with the computational storage device features, and offload only those portions to the device. And what we hope to show with that is, again, a significantly useful way to offload some of the database computation activity to the device. So these are two key designs that we are working on. We are hoping that we will be able to make these designs public, and hoping that that will enable more participants to work their ideas and see what other applications would be able to use computational storage effectively, and in turn enable the industry to make these ideas more available to storage devices as a whole. So That is basically what we wanted to do. Just to mention again, the bulk of the development work on this, we are doing it in partnership with Ant Micro. You might know some of them probably on this meeting also. So in conclusion, we have a compute accelerator from Western Digital is a very versatile device that offers compelling solutions for video transcoding and ML inference engines. And we would like to make the NVMe plus eBPF, the TP4091 implementation available to the industry as a whole to further speed up the work on these applications. Again, these devices now available for if you want to play with it, and you can contact me at anand.kulkarni@wdc.com, and we can discuss opportunities further.
Thank you, and I appreciate
that is all I had. Yep.
Yeah, no, thank you so much. A very informative talk. I really appreciate you preparing it and coming to share with us today. I just was curious. I was interested, I guess, probably because of my background at Oracle and some work that was done there relative to database acceleration. So I am intrigued by the idea of moving the acceleration closer to the storage. So as you may know or may not know, but one of the things that Oracle had the Spark design team do is put in what was called a database acceleration unit directly into a Spark chip. And there were also a consideration over time, actually, of adding an embedded FPGA into that to be able to allow for more customization over time. But that part at least never came to full fruition. But I'm just curious as to how you are determining the relevant queries from a given database to implement in the actual hardware, if you can comment on that.
Yeah, so there is essentially what we believe is that there is a I mean, of course, the scope of what SQL can do is huge, and there is a possibility, or there are, I think, ideas out there that involve implementing a full SQL query handling in FPGA, but that is not what we are trying here. We are doing, we are only looking for portions of the SQL that can be effectively handled in an FPGA of the size that we have available to us. And there are mechanisms in on the database application side to parse out the SQL into pieces. And when we detect pieces that can be effectively handled, only those are handed off. And there are optimization mechanisms in the database. I think they call it a scheduler in the database that you probably are more aware of. But there are ways by which the scheduler can actually rework the schedule such that we can pick out the portions that can be offloaded and send them early to the device, so that bulk of the filtering is done in the device before the more complex SQL portions can be handled in the host itself. Right? That is the approach that we are looking at. I don't know if that clearly answers it. So we are not actually trying to implement a full SQL query here, because that would be probably be a task for a much bigger FPGA, and it will still be limited to what it can do. So we're cutting and slicing the problem down to portions that can be handled easily by this device, but still give an effective speed up to the overall application.
No, thank you. Appreciate that. Just one other question from my side. I was intrigued that in terms of splitting the machine learning model I'm surmising that's done by your software partner. I can't recall the name. I apologize for
It's
that.
mixology.
Yes, that's it. Yes.
Yes. So what was the question? Sorry.
I noticed there was some comment in the presentation about partitioning the machine learning model. I just was curious, is that done by their software or just how that's done?
Yes, that is handled by the software. So the mixology has a software called Zebra. That is the one that is available. That is partly run on the host machine and partly run on the FPGA device. And the portion that runs, the pre-processing that runs on the host machine has the ability to parse the ML graph and partition that into portions that can be offloaded to the FPGA, and it does. But for the bulk of the standard machine learning models that we would use for video classification and image classification, bulk of the models are run completely on the FPGA, and is only for some outlier models where you might come across portions that cannot be run on the FPGA. Only for those, the splitting of the graph is carried out, and some portions will be run on the host.
That's great. Thank you for that. So I don't have any further questions. So with that, thank you so much for your informative talk. I really appreciate your time and sharing.
Thank you so much. Thank you. Bye.
Yeah. Bye-bye. So our next talk is entitled Towards Open Source Models of Cryogenic CMOS, and the presenters are Brian Hoskins and Pragya Shrestha from National Institute of Standards and Technology. They're both research scientists at the NIST group there, and they're located in the East Coast. So Brian and Pragya, if you want to share your screen.
Yes, hello, can you hear us?
Yes, we can hear you, and we see your display too.
Great, so I'm here. I'm Brian Hoskins, and I have Pragya Shrestha with me. Pragya, why don't you take it away?
Thank you for letting us talk a little bit about what we're doing in the field of cryogenic electronics here at NIST, and we're very excited to share the stuff that we're doing with you all. And I'll start off the presentation with a little bit of background about why cryogenic electronics, what are the problems that we're trying to address here, and then Brian is going to talk more about what we've been doing towards open source models later. So before going into the details, just a little bit of background about NIST to people who may not know what we are. So it's a National Institute of Standards and Technology, and it's a national lab, and the mission being to promote US innovation and industrial competitiveness by advancing measurement science standards and technology. So when I go forward, you'll know how much we emphasize in like reliability and accuracy of measurements. Moving on to cryogenic electronics. The reason why we went into this cryogenic electronics project is because of its application, broad application space, starting off with high performance computing. So basically you can reduce the temperature of the electronics that you have and boost the performance of your electronics. So usually it's in the temperature range of about 77 Kelvin or so. The other electronics is the electronics that would support the low temperature source and sensors, like in the case of satellites and space for space missions. But the biggest application space is the quantum computing that we're working towards, basically, because this has been the most important application space that's pushing the cryogenic electronics research all over the world. There are a lot of big government putting money into it, a lot of companies also working towards it. So in this particular case, the quantum computers have these basic components known as qubits, which are at really low temperatures in the range of millikelvin or so, and it's still classical electronics that controls these qubits. So just going into a little bit more detail into each of these applications, the first one being high performance computing. So this idea came about because in the past, researchers were looking at the material system and the devices, transistors and stuff at really low temperatures to understand them better. And what they found out was these materials had better performance at lower temperatures, like higher mobility, which meant that you can use the devices for higher speed. And of course, the noise would be lower for lower temperatures. The reliability would also be better because there would be lower thermally assisted degradation. You would also reduce susceptibility to latch-ups. And the power consumption would also be low due to a lower power supply, lower supply voltages. But these are all mostly, some measurements that make us think that, okay, high performance computing is something that can be done with cryogenic electronics. But a lot of research is being done to actually see if it is actually feasible or not. In the case of electronics that support the low temperature sensors, the field are like the space missions, especially a lot of physics, science stuff for particle physics that uses the low temperature sensors. So these sensors are subjected to low temperatures for various different reasons. The first one being the temperature at which it is really the environment of the temperature, the environment at which this sensor is at a really low temperature, for example, in the space, or in this particular case, you can see that the sensors might be in this huge tank used for particle physics experiment inside this argon chamber, which is at the temperature of 80 Kelvin or so. Or the sensor may be subjected to low temperature to obtain better sensitivity. For example, in this case, they are counting photons, and the sensor has a temperature-dependent background, which is as the temperature goes down, the background reduces, and so does the sensitivity improves. The other one is where the low temperature is required for the sensor to work. For example, in this case, which is SQUID, superconducting quantum interference device, which is a very, very sensitive magnetic field sensor, which can detect things like brain activities too. But superconduction is required. So you have to place this structure at a really low temperature for it to work. So at present, the electronics that support these sensors are either placed away from the sensors, or if the environment is low temperature, they would be placed in a box where the temperature, you heat it to get the temperature to about 20 degrees C or so, where you know that the electronics work just fine. So, if we can find electronics that would work at low temperatures would really help this field. Moving on to the big thing, which is the quantum computers. This is a picture from Google, and they were using this to work on 53 qubits. So at present, the way how it is done is the quantum processor, or the qubits that I explained earlier, has to be at low temperatures for it to retain the information. Is at low temperature, but everything that controls it is still a classical electronic, and in this case, it's all at room temperature. You can see all of this. Now, if you want to say like, okay, I'd want to scale this system up to say tens of thousands of bits or even millions of bits, a system like this would not be feasible. You can see it, right? So what you would want to do is you'd want to actually shrink the size of these electronics and put it as close to the processor as possible. Now, before I move into what is required, I'd like to say that these qubits come in different flavors. It's not the same type of qubit that everybody uses. It can be ion traps, it can be superconductive, it can be any flavored quantum system. But in any of these cases, you'd still need a mix of AC and DC signals to control and read these qubits. And they would also require some simple digital circuits like inverters, ring oscillators, analog circuits like voltage references or low noise amplifiers. So what you would want to do to improve the scaling is you want to shrink the size of all the electronics that you have here, put it really close to the quantum processor as possible. For example, in this case, the multiplexers and demultiplexers are at millikelvin stage, and the rest are placed at 1 or 4 Kelvin stage. So that is something that seems very doable, given like very simple electronics that may be required to do this. But the problem is not the size. The size is fine. We can reduce it. We can make these circuits work too. But the problem is how well these circuits work. Because when you're using quantum computers, it comes in this dilution refrigerator here, and each of these stages have different temperatures. Down here is the lowest temperature. And the problem is the cooling power of each of these stages is different. And as the temperature goes down, the cooling power is reduced. For example, in 4 Kelvin stage, you only have like tens of milliwatts of cooling power. But for millikelvin stage, you only have tens of microwatt, which means that if you have an electronic circuit that works, you can place it in there. But if it starts to radiate heat, then it's just going to be a big heat load, and it would increase the temperature of these stages, and then you would not have the right information that you are trying to get from the quantum processor. So that's something that you'd want to keep in mind when building these electronics, which means that the specifications is very stringent. It has to be operated at really low power, and it has to be really, really efficient. And to get an electronics of such sort, you have to start right from the basics, right down from the devices and how it works. Now, in my previous slides, I was saying like, okay, these cryogenic electronics, they work at low temperatures, 77 Kelvin, 4 Kelvin. But what I did not mention was that it's not a simple thing for these devices to work at 4 Kelvin, because if you ask a device person, they would always say like, okay, are you sure these devices work fine at that low of a temperature, where you would actually see these carriers to freeze out, right? So the freeze out does occur, which means that there are only few transistors that would work. For example, the BJTs would not work or would have a big problem at these low temperatures for it to work. But MOSFETs are fine because they can account for these freeze out that is happening. For example, when you think about freeze out, it means that your carrier is inside this potential well, and the thermal energy is not enough for it to excite and go out and conduct. But in case of MOSFETs, it's voltage controlled, which means that you can now apply potential to the system to change the shape of these potential wells, and even a small enough thermal energy is enough for it to come out or tunnel through to get the devices to work, which means that the devices would work, but the operating parameters would be different. In this particular case, your threshold voltage would shift or increase for lower temperatures. Your ion increases because your mobility is better, because no scattering happening at that low temperatures. And your subthreshold swing also improves, right? So now if you look at these images, you would say like, oh, wow, at 4 Kelvin, it works really well, right? It has a good subthreshold swing, it has good mobility. So what is the problem? And of course, these are being, thought of being used for high performance computing, right? But the problem is when we put together a circuit with the information that we had, what happens is most of the time, the circuits don't work. Well, the logic circuits, they kind of work, but not as effectively or efficiently as you would want it to. But the analog circuits have big issues. And the reason behind the room temperature circuit designs working really well, but the low temperature not working is because for room temperature circuit designing, there's a lot of information that is already known. Even if there are issues at these temperatures, they already know what the issues are. So the designer knows how to get around it. But in terms of low temperatures, there isn't much information. There's a lot of data there, but not a lot of information. So let's just say we don't even know what the problem is. So let alone solving the problem, right? So that's the big gap that is there. And NIST is trying to solve that, basically to fill that gap up, to understand the devices better, the reliability of the devices better, so that we can move on to making accurate models to get accurate circuit designs for low temperatures. And we start off with a device characterization for accurate PDKs. In case of regular commercial device models, they go down up to minus 40 degrees C. And if you try to check what it does with the low temperatures, they don't really, the experimental values don't really match. because they do not account for a lot of different things that happen only at low temperatures, and they do not show up at high temperatures, like kink effects. You have subthreshold slope saturations happening below like 50 Kelvin or so. You have a lot of mismatch and variability. There's incomplete ionization mechanism that is not accounted for. So this is something that we are working towards, trying to do device characterizations to get accurate models so that these parameters can be put into it by adding the parameters or even adding subcircuits or stuff, just to make sure that your model is accurate enough for the circuit, better circuit designings. Now, I want to put a further information here that we just don't want to make the models accurate by measuring it or with just data. But what we'd want to do is we'd want to also understand the devices better a little bit, understand the physics behind it a little better, because we want to make more informed decisions, right? We'd want to make sure the extrapolating the parameters are fine. We'd want to also make sure down selecting relevant technology would be easier. And we'd also want to know whether what kind of reliability concerns is going to occur at low temperatures that we haven't even thought of, and is not even a problem for higher temperatures. And again, because NIST is a public entity, whatever information that we get is public information, which means anybody can access it anytime. So it's going to be a very valuable resource. So moving towards understanding the devices better, from history, we know that if there is a time knob in the characterization or the measurement, it gives us a lot more information about the device. So this is the first step towards that. We built a time and temperature dependent characterization setup here. So you can see here a 20 nanosecond sweep can be obtained all the way down to 8 Kelvin here. So just a reminder that this 20 nanosecond and these low temperatures were measured. It's a time-dependent measurement. It's not a frequency-dependent measurement where you put you measure it and put the data into these circuit models to get your IDVG measurement. But this is actually the current that is being measured. So these measurements are a lot more accurate and reliable because you're measuring the current directly. So these time-dependent measurements are also important to understand the feasibility of the devices if you are trying to look into some new devices or novel devices. For example, this is a simple transistor, but when operated at extreme condition, like low temperature and higher voltages, they can be used as memory. Now to check whether these are good memories or not, you would need time-dependent measurements because you would want to know how fast these can be switched. You would also want to know how many times it can switch back and forth before it fails. You'd want to know the retention time of it, how long it stays on or how long it stays off. So these are some of the things that can be done using time-dependent measurements. The last one here is something that we are working on, which is looking at the low temperature circuits characterization. This is a setup that we're building because it's not as simple as putting just a die on the cryostat. It's a whole circuit board that needs to be put in when trying to look at the circuit. So it's not that easy. And also we'd want to measure all the different temperatures. It's not like we just want liquid helium and liquid nitrogen temperatures. We would want temperatures in between too. So we want to know that the temperature is right in these cases, and we'd also want to make sure that the time measurements are also done right, because for example, in this case we were looking at the collective pulse oscillators, which had frequency in the range of like 6 gigahertz or so, with pulses in the rise time of picoseconds, right? So we'd want to be able to measure these things accurately and reliably. So these are some of the things that we are doing right now, and this is the last slide for me, and now I transfer it to Brian, who's going to talk more interesting stuff, let's say about the open source models that is being built with the partners here.
Yes, thank you. Thank you very much, Pragya, for all these important kind of technical details. Basically, NIST has historically operated as kind of a very basic science institution. And a lot of that is driven by both our mission, but also about the nature of the semiconductor industry. as it exists today. In particular, there's a lot of proprietary information that we at NIST are actually charged to protect. But one of the things we've been excited about recently is that there's been an emergence of open source manufacturable technologies. And what this is very exciting for us is that it makes it a little bit easier for us as NIST to move up the technology stack and to not only kind of study the individual transistors and devices, but to actually bring these basic scientific resources to bear to potentially promote and expand existing commercially available process design kits to support operation at 4 Kelvin. And so because of the what's now called, I guess, the Open Sky 130 process, and this great collaboration from Google and eFabless and Skywater, who we've started engaging in, we came up with a plan with them to develop models of all of the transistors and various devices in the Open Sky 130 PDK and develop data at 4 Kelvin so that people could potentially begin to design in this space. And so what I'm about to describe is some recent work in that effort where we've been partnering with some university partners, especially at the University of Michigan, as well as some important NIST contractors such as ADSR, an Israeli design firm, and perhaps most importantly, CoolCat Electronics, which is a long-time NIST partner organization. And I'd also like to take a moment to recognize all the various contributors like Mehdi Salagain, Tuong Zheng, David Fleischer, Akin Akhturk, Duet Marhaban, Tim Edwards, Tim Ansel, and the other guys at Google and at Skywater. And so what we're targeting in this project is gathering lots of raw data, providing fitted models based on modified BSIM, but hopefully by providing the data to the public and to the NIST scientists, maybe developing a whole new generation of models, studying and understanding basic devices, especially primitives, and hopefully growing and developing a library with the community of silicon-proven IP that will work at 4 Kelvin and can be used to grow and expand the emerging ecosystem in quantum information science. So with that in mind, we have to start at the beginning, and that's with a test structure interface. And so what we started with is a plan to create a single die with a very high density of probes. And when you consider this kind of parametric test structure interface, what you typically want to do is have something like a 40 by 40 micron pad with a regular spacing, in this case, 60 and 80 microns, where you probe at the probe locations and you find a way to compact or compartmentalize all of the various test structures to fit into the space in between the pads. By having this kind of regular tiled interface, which is particularly designed for kind of low frequency, low current measurements, as can be extracted from a conventional probe card, we can not only set ourselves up to be able to measure and generate individual devices, but potentially to produce large quantities of data from large distributions of devices, which can then be released to the public and be used not only for the most basic circuit simulations, but potentially for more sophisticated things, taking into account device-to-device variability. Now, once we have our test structure kind of understood and we want to find a way to fit everything into this working space, we have to develop a system or structure of ideas that we can use to extract the most fundamental and basic parametric parameters. And so among the things that we've developed and specified based on the Sky 130 PDK are dense ganged arrays of transistors, including all the various different transistor types, thin and thick oxide, P and N-type devices, as well as native devices among the different types. We've built MOS-cap arrays designed to extract both the basic capacitance, but also the overlap capacitances of the various device structures so that we can build accurate models of the transistor, not only in their IV characteristics, but also in their capacitance characteristics. From there, we've expanded and looked at the various different back end of line elements, as well as other devices that you would find in the Sky 130 PDK. So we've built various Kelvin measurements for things like the precision resistors, as well as line and via resistances, so that we can accurately model both these additional analog elements, as well as the parasitic resistances in between these lines. Among the other kind of back end of devices that we've considered are the MIM caps, as well as various diode modules, which come in various large plate designs, as well as dense array designs. So we can account not only for the body effects, but also the stray and edge effects. Now, once you've extracted these types of very basic validation parameters, parametric parameters, it's important to also have structures on a good test die, which include validation modules, or modules where we use this parametric data to make predictions about what actual circuits will behave like. And so for our starting type of validation model, we have one of the simplest validation circuits, which is a frequency divided ring oscillator. And so once we've done our basic parametric extraction and we're able to update the PDK, we can model the parasitics as well as the IV characteristics of the transistors and the inverters in the system. And we can use those to predict the oscillator frequency. And what we're going to do is we're going to use our predictions to validate the performance by seeing how well actual ring oscillator designs compare against our simulation. Now, because we have a parametric interface, which is designed for this high density of interconnects, we didn't specify something that would use like high frequency GSG probes. Rather, we're using the CMOS to assist us by doing these enhanced parametric measurements, where in particular, in partnership with the University of Michigan, we built our 144 stage ring oscillator design with a NAND gate control to be shunted into a 1024 frequency divider. That way we can bring the frequency down out of the high frequency range into the low frequency range, compatible with a traditional parametric probe card interface. Now, how well is this going? Well, I would say it's going pretty well. We've been able to put together with our partners a manufacturable DRC clean resultant test die, which had, besides the specifications done by the NIST scientists in CoolCAD, we were able to get layout from our partners at ADSR in Michigan. And our resultant test die, which fits nicely inside of a Caravelle frame in one of the available Sky 130 MPW tape outs run by Google, we were able to fit something like 1,400 pads with hundreds of transistor test structures, 30 different capacitor test structures, 24 ring oscillator structures, 18 line and via chain modules, as well as 7 diode test structures, and a few other goodies in there that will allow us to create a fundamental basic set of primitives, which can ultimately be used to build realistic models. And of course, you can, of course, everything's open source, so you can go and take a look at the GDS file. And down the road, we'll be providing an archive publication and some other specifications so that you can go into the details if you wanted to replicate this or experiment with the die yourself down the road. So this die is, very real. It's a series of DRC clean designs. You can see all those concepts I was saying. They've been laid out in reality. In particular, ADSR was helpful with the transistor, MOSCAP, and precision resistor arrays. The team at Michigan, using things like GDS Factory, was able to produce some of the other line and via chain resistance primitives. And like I said, those diode modules and MIMCAP modules come in flavors with both full body designs as well as discontinuous designs to help us extract edge effects. So all of these structures, you're more than welcome to go and take a look. A lot of the designs have been borrowed from typically used structures that you might find in any handbook on CMOS fabrication characterization. The validation modules especially, I'm pretty excited about. They were mostly constructed from standard cells using a bunch of different inverter classes of standard cells in the Sky 130 library, as well as some OSU, Oklahoma State University standard cells, which have been developed in Sky 130. And so we're going to have a really nice time being able to check and validate the performance of our various different models by seeing how well we can do these predictions. Now, hopefully, we'll be looking at expanding our validation model set, in particular to include all sorts of new designs that we're going to get from the community, such as things like amplifiers and other analog circuits, and hopefully down the road, some digital processors. Now, that being said, this die will take a few months to reach us, and time is of the essence. And so if you were wondering if Sky 130 works at 4 Kelvin, I can tell you the answer is that it does, because we partnered with Google and Skywater to gain access ahead of receiving our test die to other test structures that they have available. And we've already measured more than 100 transistors at 4 Kelvin and begun the process of analyzing and fitting the data. And hopefully this early sneak peek models will be available soon so that people developing in the OpenSky 130 can potentially get a head start on designing circuits that would have a really good chance of working as predicted at 4 Kelvin. So we're really very excited to see how we can grow this ecosystem of computing, both classical digital computing and analog electronics down at the 4 Kelvin stage. Now, I don't know if you have any last comments for us, Pragya.
So this slide is just basically a reminder, like there are a lot of different pieces that needs to come together for the cryogenic electronics to be successful. I've spoken about most of them, and there'll definitely be stuff that will come along in future that will have to be worked out. I did not talk about packaging, but it's something important that we are thinking of working on in application and testing sites as well. Thank you all for listening, and would be happy to answer any questions.
Hey, Pragya and Ryan, thank you so much for a great presentation. Really appreciate it. Very informative. So I did have a couple questions, and actually you just have, I'll start with this one since you just touched upon it there, Pragya. But in terms of packaging, I'm just curious what you're looking at in terms of providing packaging for semiconductor working at near 0 degree Kelvin type temperature.
Also, this is something that we've just started to work on, you know, it's just thinking about it. There would be interconnects. We'll be thinking about, especially dealing with the material system. That would be the best to give a good thermal and electrical contact as well at these temperatures. Those are some of the things that we're thinking of, like heterogeneous integration as well. You know, those are a few of the things that we're thinking of. But we have, just to tell you that we just started this thing since we, you know, putting the testing structures together, we realized that this is going to be a big problem moving forward.
Oh, that makes total sense. No, I appreciate that. So one of the other interesting thing is I've been in the semiconductor industry for quite some time, and so I've saw the evolution of copper interconnect from aluminum years back, and then going to SOI-based technology as opposed to bulk, and of course from to to FinFET-based transistors. And each of these different changes has required updates to parameters that are put into the underlying SPICE models or silicon models, if you will, right? And then also oftentimes have required updates or changes to the simulators and then associated higher level EDA tools, such as like static timing analysis. And I just was curious if you're seeing a need for some update to the underlying model parameters that you capture, and then also if there would be impact on the associated EDA tool chain.
That's a great question, because these are, I didn't want to go into the technical details of it earlier, but these are some of the things that we would definitely want to look into, right? Depending on the technology, like you mentioned, like the FinFETs or SOIs, you do have different response to the temperature also, right? Those are the things that you would know only if you start measuring, especially the time-dependent measurement that I was talking about. It would give us a lot more information now, like in terms of self-heating, that might be a problem, right, for FinFETs. It might be bigger of an issue for low temperature electronics. So those will have to be put in place. That is definitely right. Thanks for the question. That's a very good question.
I just related, do you think there will be a different, as we've migrated through some of these different process technology attributes over the years, there's also been changes in circuit design techniques. In fact, I've seen processor design teams migrate from, from full custom domino type logic to complementary pass transistor logic to full static, depending upon the underlying process performance parameters. Do you expect to see changes possibly in circuit design as a result of this?
Yeah, definitely.
Okay, no, appreciate it. Any other questions from the audience? Okay, well, thank you so much for a very informative talk. I really appreciate it.
Yes, thank you so much for inviting us.
Oh, no, it's great. And our last speaker today is Tim Ansel from Google. So he's a longtime Googler, open source contributor, and very strong champion of many different things from Google, including Python, as many are familiar with, and also, of course, now is a strong advocate for building an open source hardware design ecosystem. He's the co-chair of the RISC-V SOS CPU interest group. So with that, I'd like to introduce Tim to the audience. So Tim.
Hello, are you able to hear me?
Yes, we hear you and we see your slide too.
Great. Give me a second. I'm actually coming live from the Skywater Foundry today. I'm currently visiting at Foundry to continue to evolve some of the things that I've been talking about and other people have been talking about today. Originally, when I presented or like put forward this talk, I was going to focus mainly on the who had contributed to the shuttle program and that type of statistics. But as I went through working on this talk, I realized what I ended up with is more kind of a, here's the results of what's happened in the last year for our no-cost shuttle program. And so this talk is going to probably be a little bit different to maybe what people expected, but hopefully it will be still quite informative. So the slides can be found at that link. And I want to reiterate that, you know, I'm a software engineer. I've been at Google for 14 years. I've been doing open source for since 1994, but I'm not an ASIC designer. I've not got a huge amount of ASIC experience. And these days I spend most of my time actually doing budgets and reviewing, you know, proposals and these type of things. Pretty much everything I'm presenting here is not work I've done, but work that has been done by people in the community, by various contractors we've worked with and research groups we've partnered with. To first take a step back, why is Google interested in this whole open source ASIC world? And the reason is because Google runs on computers. It runs on a huge amount of computers, and pretty much everything we build these days has a huge demand for compute resources. And with Moore's law kind of slowing down, we are seeing that, you know, we're going to need to find new ways to meet that growing demand. And that growing demand is growing extremely quickly. We don't just need 10x, we need 1,000x increases. And there, as you can see from Moore's law, the number of transistors is still going up, but a lot of the other things are not going up. And we still see plenty of room for improvement, like a 63,000x speed up just from moving some instructions from Python to SIMD optimizations before we even go into hardware. And so we're looking for another increase in performance that way. And to do that, we need faster, cheaper, and more custom silicon. And an example of where we've been successful with this is with the TPU, but in designing the TPU, we found that there's an increasing gap between what process node is able to achieve, and there's skyrocketing costs in doing silicon, which is actually the total opposite of what we want. We want it to be faster, cheaper, and easier to deploy silicon. And we want this massive increase in doing silicon. And so what we're looking here is to increase the number of users, which brings to another interesting aspect here. In the US, there are about 70,000 computer hardware engineers, which is growing 6% year on year, which is actually a pretty good growth rate. But if you look, there are 800,000 software engineers, and that market is growing at 30% year on year. So really, we need a lot more of these software engineers to do hardware. And we want to convert those software engineers into hardware engineers, and we want to speed up the iteration loop between developing applications and developing hardware description that's suitable for those applications, and then implementing it. Google published a paper called The Hardware Lottery, which talks a bit about how there's this feedback loop, which is preventing us from exploring a lot of different options. And we want it to make it much easier for us to break out of those predetermined solutions. And what was blocking open collaboration in our eyes was a couple of things, but one of the biggest was a manufacturable PDK that was fully open source. And so I put together this idea that if you created and released an open source PDK, you funded EDA tool integration, and you run a silicon realization program, that you would get a massive increase in activity in this space. And the first part was an open source PDK. The second part was EDA tool integration with a large number of open source tools, which can be viewed in this way, or it can be viewed in a separate way, looking at how you connect to various things, and a no-cost shuttle program. So that was three things that we needed to do to succeed here, was the hypothesis. These three things. And we really thought that the open PDK would be a strong driver in improving both HDL designs and EDA tooling. And so if you know anything, you know that it's been a while since we started doing this. So how is it going? Well, in June 2020, I did the announcement around the Skywater program. And we released a 130 nanometer PDK that was manufacturable here at Skywater, that didn't require an NDA. It was available on GitHub and under a real open source license, an Apache 2 license. And you could just go there and clone. And 130 nanometers is a reasonably old technology, but the Skywater process is actually pretty all-inclusive. It has a lot of different features. And what we discovered is in the week after we had released the PDK, it had almost as many stars as hardware projects like Yosis and Chisel that have been around for 5 to 10 years. We're also seeing now that every 2 weeks, we're getting almost 1,250 unique users visiting the Skywater PDK repository. And we have 2,800 members now on the Slack discussion channel where you can go and discuss the PDK. And so that was a pretty strong signal that there was something really good going here. And so we had the Silicon Realization Program, and since then, we've done a lot of work in that area. But one thing I wanted to point out is, I mentioned this in the original talk, is that this is all new and things are going to be bumpy. You know, we have a new PDK, although the process technology itself has been used and available for a good 15, 20 years. This open source PDK was new. A lot of the EDA tools, even though they have been around for a long time, have only just been integrated with the Sky 130. And this was the first time we had run a Silicon Realization Program. Every part of this hypothesis was new. And so the expectation that things were going to be bumpy should be well understood here. But that's kind of why we're doing this. We're trying to push the state of the art forward. We're trying to enable these things to actually, you know, attempt to do this. And it's okay if things don't work the first time. If things, you know, take a couple of attempts to work, that is fine. We want to see people iterating and pushing things forward. And so the plan kind of looked like this, that we had the first run at the end of 2020, and then we had a couple of runs in 2021, and there'll be more in 2022. And so if you put them on a timeline, this is kind of where the whole Silicon Realization map looks like. And so in 2020, we ended up doing 45 unique tape outs as part of this program. Then in 2021, we did over 200 designs once you put together the open MPW program run by Google and the ChipIgnite commercial program that you know, eFabless launched last year. And we've already had one shuttle run in 2022, and who knows how many submissions we're going to get this year, because for the first shuttle run, for the first time ever, we had more submissions than we had slots. And so that's pretty awesome. But when I'm talking here, I'm talking about people submitting DRC clean, ready to manufacture chips. But there's always a question of, do the chips work? Well, sadly, in silicon manufacturing, you have to wait until they're actually built and sent back to you. And so where we were at for a long time was we got silicon back from the initial test designs and they were working. This is what gave us confidence to launch the MPW program. We had 5 test designs and a majority of these worked. These were the Strive chips that Mohammed Qassam talked about in his dial-up talk series. And so with that, 5 working chips, we moved forward with the MPW program and had MPW1 sent off for manufacturing, and then, you know, launched MPW2. Sadly, MPW1 took a little bit longer than we'd like to get back. As well, ChipIgnite 1 was sent off to be manufactured. And we were getting close to finishing MPW2 and sending that off to be manufactured when the silicon for MPW1 came back. And so this was pretty exciting. We had the first silicon back from our MPW program, but when we got it back, we started to notice that things weren't working as expected. We discovered some issues in how the design was put together that was preventing the solution from working as intended. And in many cases, many silicon experts told us this design was fatal and that there would be no possibility of getting working chips out of MPW1. And this is an important milestone for the program because it really shows the importance of why we need to build real silicon. There are lots of people who had built fake silicon with these tools, but until you actually build real silicon, do you know if this solution will actually work? And so with these chips coming back in a less than perfect stage, we quickly put a hold on MPW2, which hadn't started manufacturing yet. So MPW2 was in the process of getting prepared to send off to get manufacturing, but we had caught it just in time before it had been off to manufacturing. And then shortly after, MPW3 came in, and we held on to MPW3 until we were able to better understand the fix for the problem. But unfortunately, ChipIgnite had already started being manufactured. So this silicon that eFabless was making was already in the process of being manufactured and had a known issue with it. So that required some very ingenious engineering from the team at eFabless to do a fix to the design by only changing the metal at the top layers, which hadn't been manufactured yet. And Mohammed Qassam gave a very interesting talk about how they were able to solve this problem just using a metal fix. And the talk is deceptively called Making Open Source Chips Work, but it really should be called How to Fix a Chip that is already half manufactured, which is a really exciting thing to see happen in the open that you can go and look at. You can go and look at how their fixes were made and replicate that result. And for some reason, this slide isn't showing up, but they were able to create a metal layer fix that they believed would work for ChipIgnite. At the same time, the team also was looking at how do we proceed with MPW2 and MPW3, and they created a different fix that was much more a real fix to the problem and sent those two off for manufacturing. At the same time, these chips that were in MPW1 that were supposedly never going to work, it turns out that some people in the community didn't get the message and actually started making those chips work. It definitely required a lot more work than we would have liked, but it actually showed that even with the somewhat serious issues that MPW1 had, the community was able to get value out of this tape out. And in fact, they got some of the chips working well enough that Matt Venn was able to verify that all his designs on MPW1 worked and now has a clock on his desk powered by the first ASIC he ever made. And one of the really cool things about Matt Venn is he'd never done IC design before this program started. And so this is a really awesome example of what beginners and people with different backgrounds can bring to this field who don't have the preconceived notions that maybe industry experts have. And so what we ended up with is that the MPW one had issues, but solutions were found. eFabless were able to create a metal layer fix for their ChipIgnite, and they got silicon back for ChipIgnite 1, and it turns out their solution worked. Western Braun was able to demonstrate that his solution on ChipIgnite worked correctly without the issues needed with MPW1. And in fact, eFabless were able to work with Stanford, who had a large number of chips on ChipIgnite, to get pretty much all their chips that didn't have errors from the design side in it working. So where we are today is that we have those 5 initial test working ICs. We have the chips back from MPW1, which work with a bit of effort. And we have the chips that came back from ChipIgnite that are working pretty well, thanks to that metal fix. And very soon, we'll be getting back the chips from MPW2 and MPW3, and we're excited to see the results of that. And hopefully MPW2 and MPW3 actually work, and we see some very cool results from that. The other thing, though, is all that silicon we got back has been tested and working like characterized. So one of the test designs that we did in those 5 initial test designs was a Open RAM test chip. And Andrew Zonnenberg has a really good YouTube series interviewed from Matt Venn about his work to characterize Open RAM, and there's all this data is publicly available. Anybody can go and try and replicate his results. And we're waiting for the chips to come back from MPW2 and MPW3 to do the next stage of Open RAM characterization. As well, this seems to be a duplicate slide, but we have silicon back for these things. And with silicon back, we can start doing imaging even if chips don't work. And so John McMaster has done a bunch of imaging of the silicon. I gave a talk at the Open Tape Out conference about his imaging. You can go and look at SEM images of various parts that he's done. We're now getting SEM images of cross sections. And so you can see here how a SEM image of a cross section of the Skywater process technology compares to the actual diagram that is found in the PDK. And these are publicly available that anyone can go and look at and compare. And we're hoping other people will produce these type of images and share them with people. A really cool thing here is this is Matt Venn's design. You can see the GDS that is rendered on the README file on the right there. And on the left, you can see an optical image of his IC. And you can see it looks very similar. And this is super cool that we actually have both the GDS and imaging of a design. As well, Brian in the previous talk talked about, for example, the test tiles that are being used to develop new characterization of the process technology. Here you can see some imaging of those tiles, and we're very excited to get that raw data and build things like new, better, more advanced SPICE models. And when I say we, I mean the community. I'm very excited to see if there's a better way than the current BSIM models for simulating this type of result. And can we do a better job than just doing standard BSIM models? Well, you'll be able to cross-compare your results against the real experimental data, not just against SPICE. As well, we have added ReRAM since MPW4 as a default option that is available on these runs. So you can now play with ReRAM on the Sky 130 process technology. I'm really interested to understand how ReRAM interacts with things like cryo-cooled temperatures. Does it work? Does it fail? I don't know. I would love to see us get to that. I also want to come back to one of the key things we've discovered is that this open source solution has really enabled a huge number of first-time designers. I believe 60% of the designers on MPW1 and MPW2 had never done ASIC design before. As well, on MPW2, 1/3 of these developers self-identified as software engineers rather than hardware engineers, which I think is another really cool, exciting development. We're also seeing a wide variety of different types of designs, and this is barely covering the wide variety of designs we're seeing now. We've also seen eFabless launch their ChipIgnite commercial program. So if you don't want your designs to be open source, you can use the same open source PDK and open source tools, but keep your designs closed. And this is a massive drop in the cost required to do ASICs. Then has also enabled you to take multiple projects and fit them in a single tile. This again dramatically drops the cost of doing ASICs and enables this huge surge of new people who have never done this stuff before. So what's next? Well, this year we'll be launching a second foundry, and we're hoping to have new programs, one on an advanced 90nm process node and one on a budget 180 process node. And we're also looking at cloud-based access to advanced PDKs. You already heard about some of the awesome things that NIST is doing in this space that we're partnered with them. And if you look at what Open Road currently supports, well, Sky 130 is a really important node because it was the first. But we are hoping to see things like Sky 90 bulk and Sky 90 FDSOI, as well as maybe something like GF 180 and GF 130. These are old process nodes, but what about more advanced process nodes? Well, we're trying to figure out how we can provide cloud access to proprietary PDKs like GF12LP and Intel 22 FFL. And when doing this, the reason these are selected is because GF12LP is the best supported advanced node process technology by Open Road. In fact, the University of Michigan has actually taken out a chip on GF12LP, which I believe they've got back. There's also the Intel 22 FFL, which is also somewhat supported in Open Road. And that is again why that technology is of interest to us. It's the fact that open source tools support it that make it interesting. And ultimately, though, we're looking to a future where we need a lot more portability between things like process nodes. If you look at the variety of stuff that Open Road plans to support, with this, it gives us a lot more ability to have cross-process portability, cross-foundry portability, and even things like cross-technology portability, where we end up with a truly portable solution where you don't have to reinvent the wheel for every single design you do. And an example of this portability is if you look at the EDA tooling integration, a group that has really pushed this further than anybody else is the analog generation done by University of Michigan and MEDI at the University of Michigan with the OpenFA SoC. And we know that analog is one of the biggest sticking points in developing new ASICs. And this was a part of the missing IP point that I pointed out in my original paper, and why I've been investing in these analog generators. Originally, FASOC was based around the proprietary tools like Synopsys and Cadence, but that restricted the people who could use it to a very small number of people, mostly just the University of Michigan. And so one of the first things we worked with them to do was to create a fully open source enabled flow. The tool will still support the proprietary tools, but by having a fully open source flow, it enabled us to do the collaborations like what we did with NIST. And they have used this very successfully to do tape outs at both Sky 130 and GF12LP. And if you look at those two process technologies, I don't think you can get a bigger delta in difference here. One's a 130 nanometer planar bulk process, and the other is a 12 nanometer FinFET process. And by using the open source tools and this scripting generation approach, they've been able to target both these processes. And they are silicon proving a lot of these examples. They have LDOs, which are very interesting to supplying your system. They have PLLs. And you can see that with the LDO, they have taped out on multiple different process technologies and have been iterating on their generator to improve their performance, and it gets a better result on both the Sky 130 and the GF12 solution. They also have ADCs that they're working on. And if you want to compare, for example, they did this tape out on GF12LP. You can kind of see this test IC here. And it has some DC to DC converters and a fully mixed signal SoC. And then they replicated a whole bunch of that design on Sky 130. And they were able to do this significantly faster, even though they had originally developed this on GF12LP. And they have done measurement of these results and provided quite detailed characterization of this result on Sky 130. And this is super interesting, I think. It shows how you can actually get interesting results on these older process technologies that directly connect to stuff that's happening at modern process technologies. They were also able to tape out, for example, the same OpenTitan SoC based RTL using Open Road on Sky 130. So this is another thing that is portable between an old process technology and a new process technology, complete with analog that's portable from the old process technology and the new process technology. And in the process of doing this, they actually had to add new features to the Open Road tooling, which benefit all users of those tools. And this is just another thing. And so this is really showing that this portable analog is possible. And the great thing about this is that GF12LP is significantly more expensive and significantly harder to get access to than Sky 130. And you can see all these connections from these two very different process technologies. So there's also the Berkeley analog generator that we invested a bit in. And as part of that, there is the BAG3 primitives available. But sadly, at the moment, that still requires closed source software and the proprietary S8 PDK. And so that's been a lot less successful than the Open FASOC work, which has had multiple tape outs and has a fully open source flow. And so that's kind of an interesting proof point. If you have any questions, you can email me here. And I think that's the end of my talk.
Hey, Tim, thanks so much. That was a very informative talk and update. I really appreciate it. So definitely some exciting work that you are championing here in the open source community. The one question, as you know well, I've been in the industry for a long time, and I often think about the attitude that the hardware engineers have, which I have to say is unfortunately ingrained in them from day one. And this is basically that failure is not an option. In other words, that once you tape a chip out, that it darn well better work. So one of the things that you're helping to champion here is really to change that type of attitude and explore new ways of thinking. I'm just curious if you might have any thoughts about how to help move that along.
So I totally I think the hardware people have been put in a really difficult position. If you're doing a tape out on 7 nanometers, that chip better work because you just paid millions of dollars just for your MPW run. What has been lacking in this industry is easy and cheap access to these process technologies that aren't so expensive. It's much better to fail on 130 nanometers than it is to fail on 12 nanometers, which is also what the Sky 130 process technology, example showing, the problem that was found with MPW1, I would much rather find that problem on Sky 130, where a tape out is, 10x cheaper, than find that out when we finally do a GF12LP tape out, right?
Right.
And so it's about reducing the cost of failure and utilizing what resources we have access to, right? These old process technologies are old, right? They've been around for 20 years. Everybody should be using them to test theories all the time, but there's such a huge focus on, I only care about 7 nanometers, that you've ended up being a very risk averse, right? Because you can't fail and you have no history to build on to say, look, well, it shouldn't fail because I've done it 10 times on Sky 130 first, right? I have a lot more confidence in the results that OpenFASOC gets for GF12 because I'm able to see their results for Sky 130. There are always going to be failure, right? If you're not getting failure, then you're not pushing hard enough the boundaries of what you can do. And, you know, I'm only new to Silicon Valley. I've only been in Silicon Valley for about 4 years. But one thing I have really noticed is that they really understand this idea that the next big thing looks like a crazy idea, because if it was obvious what the next thing is, you'd just be doing it. And so you need to enable a lot of crazy ideas, and most of them are going to fail, right? Because you need to enable that one crazy idea, which totally looks like every other crazy idea, because it's the big thing, even though all these other crazy ideas are really crazy and, you know, are not going to work. And so, you know, this very much is a mentality type of thing. As well, by increasing the number of people here, though, like a lot of the people, you know, that I talked to in industry, when they looked at the stuff that like Matt Venn and TNT did, they're like, oh yeah, you could totally have done that. I've done that for previous chips when I've been in a bind. It was kind of a, oh yeah, okay. If you're willing to put in that effort, you could solve these problems, but I assumed you weren't willing to put in the effort. And so I think that's also a really interesting thing here, is that people underestimate, you know, what can be done when that's your only option. And so, you know, this I think is a really interesting thing here as well.
No, I appreciate that. You know, one other, I like your thoughts here. You know, wanted to see what your thoughts were about getting more people involved in open source EDA. So, you know, a number of the universities, and you mentioned Michigan, and, you know, I know they do a lot of great work in EDA and training young engineers for that. But what, in terms of trying to get more people interested in EDA development, what do you think we might need to do in that regard?
I think the big thing is we need to stop isolating EDA from the rest of the software development world and start treating it just like any other piece of software development. There's, you know, EDA problems aren't easy problems, don't get me wrong. But, you know, it's not an easy problem to index, you know, the world's internet. It's also not a easy problem to sequence the human genome and these type of things either, right? Like, hard problems are everywhere. The more we can get and utilize, you know, shared knowledge, the more likely we are to move this forward faster and take advantage of a lot of work that other groups are doing. It turns out for like software development, in many cases, 90% of the work in software development has nothing to do with the domain you're working on. It has to do with how do you package the stuff? How do you get it onto the user's workstation in a way that it works? And, you know, there are many different competing technologies to do this, and it's a billion-dollar industry. You know, containers and cloud-based stuff is huge. And we need EDA tools to work and integrate with these solutions, because if you're reinventing just for the EDA space, it's not a big enough space by itself at the moment to have custom solutions for everything. They should be reusing, you know, things like Python. They should be reusing things like notebooks. They should be reusing things like Airflow and, you know, these other things that, you know, the machine learning people are using, the data science people are using, the geo people are using. One of the cool things I was looking at the other day is that the geo people have a really nice setup for viewing, you know, large data sets of polygons. And you know what GDS is? A large data set of polygons. So rather than reinvent a new way to view the, you know, GDS data, what we did was just convert the GDS data into the geoscience format and use their very fancy, map viewer to view the GDS. And, there's parallels there. And the people doing map stuff, that's a huge field. And they've spent lots of time, figuring out how do you cut up tiles in an efficient way? How do you deal with the fact that, you bisect polygons in a way? And their data sets, are petabytes in size in many cases, right? Like they're not small data sets. So this idea that EDA is the only group that has big data sets and the only group that has any of these problems, I don't think is the right attitude. You should, work with as many of other groups as you can. I was talking to someone recently about optical simulation, and if you look at what people like NVIDIA are doing with modern ray tracing for games, it's starting to look very similar to the type of optical simulations you need to do for very advanced optical stuff. And there's lots and lots of overlap with all these other fields.
No, that makes total sense. I think that's great. Just one final question from my side. Do you think there needs to be a revolution in EDA tool development relative to using cloud computing, or is kind of the approach that folks are taking now sufficient?
I definitely think there needs to be a revolution because pretty much every problem in EDA is an NP-hard problem, optimization problem. And so you've got an NP-hard optimization problem of NP-hard optimization problems. And the only way we can scale beyond this type of very limited heuristic-based approach is to take advantage of massive amounts of compute that are available to anyone. And, people like Google are going to try and use every spare cycle of compute we can to improve the performance of the next chip we're doing, because it makes sense to do that. This is a really important aspect of this industry, is that we need to stop doing small numbers of experiments. We need to start doing millions of experiments in parallel. And we need to collect that data and share that data, because nobody's going to have enough resources to do all the experiments across all domains at all time. Even like these are impossibly complex problems. Everybody's individual data sets is like a little point on this massive optimization space. And we need as much of it shared with as many people as possible so that we can better understand this whole space. And so really we need a lot more open collaboration, which cloud can make a lot easier. It's much harder to collaborate when you can only run it if you have the correct license or all these other type of things. So I do think there's this revolution's coming. I don't think the existing proprietary EDA tools are going anywhere. I think they serve a existing set of users really well. And in the same way, Windows continues to exist even though Linux and Chromos came about. It's definitely a case that the proprietary EDA tools are going to continue to exist. And I think they're going to explode in users as well, just as the open source, user ecosystem exploded with things like Linux and GCC and LLVM. These all, really enable more people to do cool stuff. And people are going to need to use proprietary tools for some things, but we really do need a base of open source to get people started and into the field.
No, that makes total sense. Thank you again for your time today, Tim, and an outstanding presentation and updating the community on where things are. So I think it's quite exciting. Thank you.
Thank you for having me.
Oh, our pleasure. So with that, folks, that concludes our seminar today. We will make the recording available for folks to view later on, and also the presentations too. So my thanks to all the presenters and all the hard work to put together the talks and get them out to us. So thank you again. So hope everyone has an enjoyable remainder of the day. Thank you. Bye-bye.